Hi everyone, to those of you who have joined, welcome. We're just waiting for people to jump on the call. The number of participants is just increasing at the moment, so we'll get started very shortly. Some people from Europe, it seems, so we'll also be touching on the IB and other qualifications here, but really a lot of what we say will probably be talking about A-levels, but it will still very much apply to you anyway. So without further ado, let's get started. So the title of today's webinar is PAT and NSAA, 4 concrete strategies for Oxbridge physics applicants. Okay, so who are we? I think we'll start off with who we are. Oops. So here's a brief introduction to all of us panelists. I'm Parul. I'm the founder of the Oxbridge Formula, and I'll give you a little bit of background about myself. So I studied maths at Oxford. I think Daniel was saying like 12 years ago now. So it's been a while since I was there. But after that, I qualified as a teacher, and I've been working in London independent schools for the last 10 years or so. We've been running the Oxbridge Formula for, I say the last 10 years, I worked for 10 years, and then I've been running the Oxbridge Formula for 6 years. What is the Oxbridge Formula? So we're an Oxbridge preparation company. We specifically help students with admissions tests and interviews in subjects which have a mathematical component. So that includes maths, computer science, physics, engineering, and economics. Those are our kind of key subjects, although we do have other offerings as well. So yeah, that's a little bit of introduction about me. I'll now introduce the other people on our panel. So Chris, if you can give everyone a wave. This is Chris. He is our lead tutor. You could call him a super tutor. He's very, very much in demand. And if you are lucky enough to kind of join one of our programs, although he only works with a very small number of students kind of on a one-to-one basis, he is the lead tutor on our courses. So you can get direct teaching from him during our program. We also have Daniel. Oh, sorry, I should introduce a bit more about Chris. Chris has a first-class bachelor's and master's degree from Oxford University. He's been working as an Oxbridge preparation tutor for the last 7 years, and he is the founding tutor of the Oxbridge Formula as well. We also have Daniel. Daniel is a 4th year, i.e. a master's student studying natural sciences at Cambridge currently. I believe it's Homerton College, is that right? Yeah, and his specialism is quantum mechanics. So if you have any questions about that, feel free to save them up and ask in the Q&A at the end. We have Giacomo. Giacomo is one of our tutors, and the really nice thing is that he actually did our program a few years ago. He was himself taught by Chris, and he's studying physics and philosophy at Balliol College, which is my college too, so that's really cool. Yeah, before we kind of go on, Giacomo, while you're here, I don't know if you want to talk about your experiences working with the Oxbridge Formula.
Yeah, I'd love to. So I applied and I found I went through the Oxbridge Formulas program and found it particularly useful with preparing me both for the PAT and the interview. I went on a couple of the PAT courses which really helped me speed up doing some of the questions, which helped with the time pressure in the exam. And also I did the problem solving course, which helped with that aspect, which is obviously quite important. I also had a mock interview with Chris, which was great in terms of preparing me for the interview, knowing what to expect, knowing how to answer questions. And I think that served me really, really well for the application process.
Okay, fantastic. Thank you so much, Giacomo. And these are some of our other successful applicants who have got in for physics, engineering, or natural sciences courses after working with us. So let's talk about what we're actually meant to be here for today. So NSAA and PAT. Here is what we're going to be talking about today. So firstly, what are the PAT and NSAA? When are they taken? So all the facts. How are the tests used by Oxbridge? How do they differ from A-level? And how do the questions specifically differ from A-level? And that's kind of like the what, what is the PAT and NSAA, that kind of thing. And then we're going to be talking in the second half of the webinar about preparation. So we're going to be discussing our prof methodology for tackling PAT and NSAA questions. How do you dissect a question to make sure you get the most marks possible in the real thing? We'll also be looking at exam technique. So that includes timing, the working and your presentation, and also how to check your work, preparing to sit the PAT and preparing to sit the NSAA. So that's the second half of the webinar. Right, so what are the PAT and NSAA used for? So in terms of courses, the PAT is used for physics and philosophy, engineering and material science at Oxford. And the NSAA, or some people call it the NSAA, is used for natural sciences and veterinary science at Cambridge. What you should know is that like natural sciences has two routes. There's the biological route and then there's the physical route. What we're going to be talking about in this webinar is specifically the physical route. But the NSAA, well, you'll see now. So the PAT, it's taken, both the PAT and NSAA are taken at the beginning of November, or it could be the end of October, depending on the year. But for this year anyway, it will be the beginning of November, and it's taken pre-interview. Both tests are 2 hours, and the NSAA is split into section 1, which is an hour, and section 2, which is an hour. What is tested in both of these? So the PAT tests you on maths and physics, and the NSAA tests you on maths, physics, chemistry, and biology. However, well, it doesn't actually do that, because when you do the exam, you have to pick one of the sciences. So we're assuming most of the people here, because you're here in an Oxbridge physics webinar, we assume that you're going to be doing the physics, and this webinar specifically is going to be focusing on the physics aspect. How many questions? So the PAT is normally consists of like 24 to 26 questions, around 12 multiple choice, and around 10 to 12, maybe 10 to 14 longer questions, which vary in length. So you can have questions from 2 markers in the PAT all the way up to a 12-mark question. In the NSAA, you have section 1, which has 40 multiple choice questions. And basically, you have to do 20 of the maths questions. Oh, so you have to do all 20 maths questions. And then you have a choice, as I said earlier, of whether you do physics, chemistry, or biology, and you have to sit 20 of those, as in there are 20 of each. And then section 2, now we're getting into the slightly more difficult questions, but still multiple choice, and you sit 20 of them within an hour. And these are just purely science. But the physics questions, the way the kind of syllabus talks about it, they do have some maths woven in there, although the form of the questions is physics. So physics, chemistry, or biology, but again, we'll be talking about physics in this webinar. So how long do you get per question? Well, obviously in the PAT, it depends. And you shouldn't necessarily take the number of marks to reflect how difficult the questions are. But assuming we did, a question could take anything from between 2.4 to 2.5 minutes to around 12 minutes. And in the NSAA, section 1 is kind of 90 seconds per question, and section 2 is around 3 minutes. What I should stress is that the NSAA is an extremely time-pressured exam. Something you get far longer for an A-level gets kind of condensed into a much shorter time in the NSAA, and we'll be looking at more of that later. And the other important thing to kind of mention is, do you get a calculator or formula booklet? In the PAT, you do get a calculator, but you don't often kind of need it until the very end of the question where you're just plugging your numbers in. You'll see later on today that a lot of the questions can be algebraic, so having a calculator doesn't necessarily help. And in the NSAA, there is no calculator. And I would say one thing to all students here, your A-levels, if you're doing A-levels, you no longer have a non-calculator paper. So I've seen that many students kind of lack fluency with their, I want to say mental maths, maybe mental maths, but also like just working. And I think it's a good idea to make sure that you're really kind of familiar and fluent with all that working, and you haven't forgotten it from GCSE. You also don't get formula booklets for either of the tests, and it's really important to, it's really important to kind of know all your formulas, basically. Like, they're not going to get given to you. Okay, so what is the PAT all about? Okay, let's have a look. So as we said, Chris, actually, do you want to talk about this?
Yeah, absolutely. So the PAT is based on A-level maths and physics, mostly the first year, so year 12. But we say mostly. You do get topics cropping up that are from other parts of the syllabus or just outside the syllabus. So the Oxford website says if there are parts of the syllabus which you think won't be covered at school by the time of the PAT, we expect you to work on them by yourself.
Yeah, I kind of want to stress that really. They're specifically telling you that there may be parts of the PAT which you haven't done at school yet, or maybe that you're not going to do at school because it's not part of the A-level syllabus. So why would it not be part of what kind of things are not part of the A-level syllabus? Well, here are some topics, and we assume that you haven't kind of covered these yet, so we're just going to talk about them very briefly. So one of them is capacitors. Capacitors are kind of electric components or components of electric circuits which store charge. Giacomo, what's the use of a capacitor?
They're used in flash photography. So the point of a capacitor is to store a lot of charge over time, build up this charge, and then you can release it in a very short space of time. And the application to flash photography is you can build up all the charge in this component, and then when you release it with the click of the camera, all of the charge is released almost instantaneously, producing this very bright, very sharp flash in a short space of time.
Great. Okay, brilliant. One of the other topics that you could encounter is simple harmonic motion, which again, it's unlikely you would have done at school by the time of the PAT. Daniel, what is simple harmonic motion?
Yeah, so simple harmonic motion is a regular oscillation with a fixed frequency or constant frequency. And an example of this might be a mass on a spring bobbing up and down, or a pendulum in a clock, for example.
Okay, awesome. Then radioactivity. Chris, if you'd like to talk a little bit more, sorry, radioactive decay.
Yeah, so I think you might have studied some particle stuff in the first year of physics, but the radioactive decay topics in the PAT tend to be, well, you're studying radioactive nuclei, so they're unstable nuclei, and you study how fast they decay or break up into other substances, and also the ways they do that, so the kind of radiation emitted.
Yeah, and the other things, depending on how, I presume a lot of people here do A-level further maths. If you do, and you do maths and further maths alongside each other, or if you don't do further maths, or if you're doing another type of exam, you may not have covered some of the advanced integration and differentiation, which normally comes kind of at the end of the A-level maths syllabus by the time you do your PAT, and it is often tested. So that's kind of another thing. And then there are some topics which are tested, as I said, which don't really appear in A-level at all. So an example is astronomy. Chris?
Yeah, so some astronomy topics they've asked about in the past are so questions about the planets in the solar system, questions about eclipses in the Earth-Moon system, and also questions about the kinds of orbits that planets or moons or comets or asteroids, etc., might follow.
All right, and approximations. So I'm not going to talk too much about approximations now because we're going to be looking at a whole question on approximations later on. But also geometry, it's not that you won't have ever covered this, but if you imagine those questions where you have a shape and you have to find the ratio between the two areas, those kind of things aren't really covered at A-level, and they're not really covered that much at GCSE either. So that's kind of an extra thing that you need to become familiar with because they do appear quite a lot in this exam. So one other thing which might feel a bit nerve-wracking is the fact that the syllabus isn't 100% followed. Like if you look on the Oxford website, there is a PAT syllabus. However, occasionally things do creep in that aren't technically on the syllabus. And I know, Giacomo, you had something to say on this.
Yeah, I mean, the reason they do this is that it's mimicking what life is like once you're at university. So remember, the people who write the PAT will be Oxford professors who could be your tutors. And what I've seen from the other side is that they don't care about a very narrow syllabus. They're interested in getting you to understand physics as a subject. And that's what they want to test here. They think that the people who deserve a place at Oxford who will do well are those who understand physics on a holistic level and who can solve problems rather than just follow a particular syllabus. So it's really preparing you for what life at university will be like.
Yeah, and I'd say that also it's not like a regulated exam board that's setting it. It's Oxford University, so they're taking that license, and sometimes you might get things just slightly outside of what you've officially been told you could be tested on, just as a warning. Now, also, as we'll see later on in this webinar, the style of question is very different from A-level. The questions require ingenuity, intuition, and a deep understanding. And I think, as Giacomo said, really mirroring how you're expected to think at university. Just a quick reminder, guys, if you have any questions, please do feel free to put them in the Q&A rather than the chat. And then at the end, we'll be able to kind of address all of those questions. Okay, and then the other thing is the PAT has been used for many years. It's gone on, we've had it since, I think, 2007. So it's, you know, a long-standing test. And basically, success in the PAT correlates to success in the Oxford Physics, Oxford Engineering degrees. So essentially how these admissions tests work is, you know, while they're developing them over the first few years, they will see how students perform in them versus how they perform in the actual degree. And they would have kept refining the test until it sort of has a very good correlation between the score you get in your PAT and the score that you get in, say, your first year at your degree or your final score in your degree. So that's kind of how the PAT has come about. And I think, again, it just echoes what Giacomo is saying. If, you know, this is the way of thinking that you're expected to use at university. Okay, now talking about the NSAA. So I'll hand over to Chris.
Okay, yeah, so the NSAA has just recently been updated. There was a new specification for 2020, so that's the first time that version was examined. It's also based on Year 12 A-level material, so maths and physics and chemistry and biology. It's very extremely time pressured, so you don't have much time at all for the work you're expected to do. There's a lot of questions in a short space of time. So there's these two sections, section 1 and section 2, and section 2 questions especially are often harder than A-level, particularly circuit questions, a kind of thing you might not have seen before at A-level. And also one way they make them harder than A-level is that they sometimes combine multiple topics together. So I think we have an example question here. So this is an example section 2 question, just without the multiple choice element. And if we just read through this quickly, you'll see all the topics it's got in it. So it says we've got water at the top of a waterfall, starts with 0 vertical velocity, and then it falls 45 meters onto flat rock. So it's falling under gravity, so that's SUVAT. And it says each second 40 kilos hits the rock, and then it flows away horizontally. There's an average depth of water on the rock of 0.05 meters, and then we're asked to find the total average pressure due to the water. So, okay, they've told us it's about pressure as well, so that's one more topic. But where's that pressure coming from? Part of it's from the water that's falling, being slowed by the rock, or stopped by the rock, so it flows away horizontally. So that means you need to work out the impulse in order to get the force and therefore the pressure. And finally, there's the force due to the weight of the water that's just sitting there. So for that, you need to combine volume and density to find the weight. So you can see there's going to be multiple steps, each based on a different topic.
Yeah, and I think in this one, a lot of them feel like kind of quite mechanicsy topics, but you can have quite different topics combined together in one question, which I think can throw people off a little bit. So just to say on the NSAA, this is what Cambridge say about the NSAA. The best applicants will score more highly, but only relatively few are expected to gain more than 80% of the available marks. So in contrast to A-level, like I'm guessing if you're thinking of Oxbridge, you're A-star candidates, you're consistently, or in your exams, hopefully going to get 80% in your A-levels. But in the NSAA, because of the sheer time pressure, they're not expecting as many people. They're saying only the best, the very, very best will get 80%. So just kind of, again, emphasizing that it is a tricky exam. So how are the PAT and the NSAA used? Well, as we said earlier, both exams are used pre-interview, and they're used to decide who to invite to interview. And they're also used post-interview, so combined with your interview performance to see who to make offers to. Now, Oxford and Cambridge kind of use the tests in slightly different ways. Oxford uses the PAT more to select the best candidates. So they might take the top 50% of PAT candidates and interview them. On the other hand, Cambridge kind of use a test to kind of deselect the worst candidates, if that makes sense. So they might pick the top 70% and interview them. And then Cambridge kind of uses the test with the interview performance a lot more when they're making the final decision. Whereas Oxford, because they've already kind of selected the best candidates, they don't take the test into as much account when they're making their final decisions. So that's kind of how they're used. It is a super, super, super important for me to emphasize that for physics, engineering, natural sciences, this test and the interview will be significantly more important than your personal statement. I talk to lots of students on a regular basis, and I'm like, okay, so how are you preparing for your Oxbridge application? And I hear all this stuff about all these extracurricular things they're doing and all the lectures they're attending and books they're reading, and all of that is fine. But what they really care about is how good you are at maths and physics, what your problem solving skills are like. And the way they test your problem solving skills is via the test and via the interview. So if you've perfected your personal statement with loads of extracurricular, supercurricular activities, but you can't solve the problems to a satisfactory level in the exam or the interview, then you won't be considered as a candidate. And why are these tests more important? Well, they're testing your ability. So are you fluent with the key ideas and techniques needed for the question? And also your potential. So can you tackle harder and more unfamiliar problems? So notice the difference there. The ability is how good are you with things that you should know? And potential is how good are you at things which are slightly outside your comfort zone, i.e. that problem solving. Okay, Chris, I'll hand it over to you.
Okay, so we'll be looking at an A-level and a PAT and an NSAA question on the same topic, which will be springs, because all these tests are based on roughly the same material, but they just examine it in different ways. So if we look at the A-level question, this is a 4-mark question. And that means in the exam, you'd have roughly 4.5 minutes for this number of marks. And the tasks you're being asked to do are simple numerical calculations. So part A, you're asked to calculate the work done when there's a force of 29 newtons and extension of 32 centimeters. And part B, you're asked to find the extension when force is changed to 27 newtons. So you're just given some numbers. You just have to apply a single formula, which is Hooke's law, and you're actually told it's Hooke's law. You have to remember what the formula actually is, but you're told what to use. And you don't really need to draw a picture or do any kind of working out what's going on apart from just doing the calculations. If we then move on to a PAT question, so this is one of the longer PAT questions you'd find on a paper. You'd have about 12 minutes to do this. It's worth saying here, just because you have more time doesn't mean it's not a time-pressured exam, because the question is much more difficult and the tasks are more extended. So there is still some time pressure. In this question, we do have a spring. We can see it's got a mass at the right-hand end, but also at the left-hand end, it's sort of fixed to a point, and then it rotates about that point. So this is combining two topics. It's combining springs with circular motion. And as we said, like combining topics is kind of typical of the Oxbridge entrance tests. It's one way of making the questions more difficult. If we look at the tasks A, B, C, and D, they're quite algebraic. So a lot of the quantities are kept just represented by letters rather than as numbers. And you have to find relationships between the variables rather than just a numerical answer. In part C in particular, you're asked to sketch the relationship between two variables. We won't go into what it actually looks like, but it's actually not a familiar sketch at all. It's not like it's a straight line or something. You'd really have to figure out, you'd have to do a lot of work to figure out what it looks like.
Yeah, and just to add to that, graph sketching is a key feature in Oxbridge entrance and when you actually go study. So that's something that we're going to be looking at again later on today.
Yeah, and then the last part as well is also a more difficult task, but a very different one. You're asked to, it says find a relationship between some of the variables and then explain what happens in some particular case. And so it's an explain type question. So your explanations have to be good as well. You're not just calculating.
Okay.
And then if we look at the answer, so just in terms of the format, one thing stands out, which is it's multiple choice. But that doesn't necessarily make it easier. For one thing, you only have 3 minutes to do this, and it's harder than the A-level question, which was 4.5. In this question, there's actually 2 springs, each with a mass at the bottom, and then one's hung from the other. So you'd need to sort of read the passage, figure out what it looks like, and then draw it yourself in order to do your working. So we've drawn it here. So we've got 2 springs attached. And if we read the task at the end, it says the combined length is 30 centimeters. So the information you're given is, it's not given in the most straightforward way. They don't say, okay, here's the extension of this spring, here's the extension of this spring. They tell you the total length, and you've got to use that to figure out what's happening to each spring. And typically there's kind of multiple steps you have to go through to get to the answer. It's not just one calculation. So you need to read this passage, figure out what it looks like, draw your diagram, put on all the information. You need to find the forces in and extensions of 2 separate springs. And then you need to work out the answer. You also need to make sure your units are correct because, for instance, the mass is in grams instead of kilograms, which you might expect. So there's always these small details that you to trip you up, and there's always sort of multiple steps to go through.
Yeah. Okay. Thank you so much for that comparison. So I guess the other question is, what if I don't do A-levels, or what if you don't do A-levels? So I'm going to hand over to Giacomo for this bit because he actually did the IB, and he might be able to give some further experience. He might be able to tell us more from his experience.
Yeah, as Parul said, I did the IB, and there were a couple of additional hurdles to jump over for the PATs. So there are a couple of topics in particular which don't get covered at all. They're written here. The partial fractions, pulleys, and pulleys in particular, I hadn't seen at all, and I still don't think they're on the syllabus. So those pose problems because there are particular integrals that might come up that people who do the IB simply won't be able to do unless you do it in your spare time, and that's what I had to do. And there's just no way around that. You have to, in your own time, cover these, find all the topics that you haven't covered, depending on which exam board you're doing, and cover the content in your own time and practice it in your own time. And that can pose additional challenges. Yeah,
so as well as the other topics that A-level students have done, there might be a few topics for you to look at in addition to that. The other thing, it will also impact the fact that you may not have done all of the topics might impact your interviews or the first year of uni. You might have a bit more to catch up on. So some things that aren't covered in the IB or in, for example, the Scottish Highers are like conic sections, hyperbolic trig, or matrices. I know, Giacomo, you said that you got asked matrices in your interview, so that would have been helpful if you had known a little bit about them.
Yes.
But I really wouldn't take, like, if there's something that comes up in your interview and you don't know it, it's definitely okay to say I haven't learned this. So that should be absolutely fine, but it just would have been nice. So if you are interested in learning more about how we can help you, and we actually run an Oxbridge Mastermind program. So it's kind of a 10-month program, which kind of covers the admissions tests, interviews, and problem solving in general. We have opened up a few slots for you to have a consultation with us. And the website address is oxbridgeformula.co.uk/mastermind, i.e. MM-consultation. So feel free to type that in. Chris, if you could put it in the chat now, that would be really helpful. And also there's a QR code there, so feel free to give that a bit of a scan. Really, people ask us, during part of the Q&As, what do you offer? But it's kind of, what we offer to you will be dependent on your needs, and so it's much better if you book a consultation. We can actually chat about what your needs and requirements are, and we can offer you the best solution that way. So feel free to scan that code, and we will move on with the webinar now. So now we're going to be looking at what the PROF methodology is. So we've looked at all the kind of mechanics of the no like pun intended, but the mechanics of the questions, so, of the papers, what they are, and how they're used by the unis. And now we're going to look at how to prepare. And we have this proprietary prof methodology that we've kind of come up with. And these are, P, R, O, and F are the 4 concrete strategies that we think will help you maximize your score in these exams. So without further ado, let's figure out what the prof methodology is. The first part of this is problem planning. Okay. So you might be thinking, well, what does she mean by problem planning? I've never heard that phrase before, but I bet you if I say essay planning or an essay plan, you have heard of that. So when you write an essay at school in English or history or whatever, maybe for some of you it's back at GCSE, you're always told to write a skeleton or like a little plan of what you're going to write. And then all that remains to be done is for you to actually write the essay. So you kind of know what you're going to say. You just need to actually do the writing. And a similar methodology can be applied to maths and physics problems, especially longer problems, because you can plan what you're going to do without writing down your solution. And there's a lot that you can take from a question by reading it accurately, reading the whole question through, seeing where parts link. So yeah, it's essentially knowing what you do before you start writing. And really identifying, what is this question really asking? What is it really testing me? What is the key information that I can see in this question? Or what's the key information that I know that I'll need to use in this question? And this is a really important one, especially for longer questions. How are the different parts of the questions related? If you can figure that out, that often helps with later parts of the question. And then what is the logical starting point, or what's the logical route through this question? So these are kind of the questions that we ask during problem planning. Now, we asked you to plan 2 questions. So we had one on kind of 2 masses on strings and also a graph sketching question. So I'm going to go to the next slide where you're going to see one of those questions, but I would love to hear from you in the chat. When you saw this question, tell me what some of the thoughts were that came into your mind. Someone says R with an A and like 5 H's after it. So someone's saying it was complex. Someone's saying, where do I even start? Someone says Newton's law of gravitation. Wow, a lot of people are like saying, I don't want to do physics. Oh no, one person said that. But okay, so people thought moments, simple harmonic motion, resolving forces and trig, small angle approximations, pendulum, trigonometry, resolving vectors, free body diagrams, Newton's law of gravitation, quadratic formula, Coulomb's law, Newton's law, SUVAT, trig and resolving vectors, waves, GPE, differentiation. This looks complex, perhaps trigonometry. Some people said I wouldn't even know where to start. Someone has said A equals minus GX over L. I'm not too sure about that myself, but it probably is. The resultant force is 0. Yeah, I love that. Resultant force is 0. Resolve forces tangentially. Approximations, so maybe small angle approximations, maybe the binomial. Someone's saying, is the acceleration constant? So for assumptions, somebody's saying, should we remove negligible forces? So these are all really interesting thoughts that you're coming up with. Oh, someone says circular motion. Okay, so that's kind of dried up. So you found this question quite scary, and I'll be honest, I think this is one of the hardest questions in the PAT. Okay, I mean, I've looked at a lot of PAT questions, and like, yeah, this is definitely by far one of the hardest questions we've seen. So sorry if you found it really difficult. It wasn't intended to scare you. But someone says here, removing small terms. And somebody else actually has given a formula, which we're going to look at in a little while. So yeah, it wasn't intended to scare you. I'm really sorry if it has, but we're going to go through this now, and we're going to tell you how we would plan this question. If at any point, I'm going to keep the chat open. If at any point you don't really understand something, feel free to ask, and we'll just pause and answer some of your questions, because like, this is a hard question, and I want to emphasize that. Okay. Somebody has written in the chat, sin x equals x and cos x equals 1. I think we're going to be looking at those a little bit later. But Chris, if you could just read through the first paragraph. So what we're going to do is we're going to read through each paragraph, and then we're going to tell you what our thoughts were when we read this question. Okay. And hopefully it will give you an idea of how we would tackle it. Go for it, Chris.
Okay, so if we just read the first paragraph, it says the diagram shows two spheres of mass m suspended from wires of negligible mass. The length between the pivot points and the centers of each sphere is L, so it's basically the length of the wire. The two suspension points, that's where the wires meet the ceiling. They lie on a horizontal line and are separated by distance x. The system is in equilibrium.
Yeah, feel free to read it slightly slower.
Okay. The system is in equilibrium, and we can take the total acceleration due to gravity to be g. And we're told, as a hint, we can assume that delta x is much less than L. That's what that symbol means, in case you haven't seen it before. And delta x is also much less than x.
Yeah, okay, so there's quite a lot just to read there. A lot of it is on the diagram. But yeah, Giacomo, when you kind of read through this first bit, what were the key things that you thought? What were the first thoughts that came into your mind?
Well, the first thing I can think of is, well, the system is in equilibrium. So we're expecting the resultant force to be 0. So we can start drawing on some forces here and thinking about what forces are acting. So we have two masses. So it's going to be, we're going to pretty clearly have a gravitational force or a weight force acting down from the masses. And
yeah,
that'll be counteracted by a tension force in the wire, though that'll act in the direction of the wire. So interestingly here, they're displaced horizontally by this little delta x. So there must be some sort of horizontal force here, which will be equal to the horizontal component of tension. But we haven't yet worked out what that is. I think we need to read on.
Yeah. Okay, cool. Yeah, so so what you're saying is because these masses are slightly deflected, there must be some force acting in this direction to kind of, well, it is an equilibrium. So because the tension is going slightly to the right, there must be some force to the left to balance it out, but we're not sure what that is yet necessarily. Yeah, Daniel, what did you kind of take away when you read this first bit?
Yeah, so I noticed the hint they mentioned in the first paragraph, and whenever you see a hint in admissions tests, you really should take it because they're quite helpful. So you may assume that delta x, and there's this strange sign compared to L, and then delta x with the same sign compared to x. And this sign with two smaller than signs actually means that the quantity on the left, delta x, is significantly smaller than L. Or delta x is significantly smaller than x. That's what both of those phrases mean. So this is useful because in our calculations, we might see a delta x over L or a delta x over x. And so the ratio of those is approximately 0, so really tiny. And we can use this approximation to hopefully make life easier for ourselves if we end up getting really complicated equations. So neglecting maybe some of these terms or higher powers of these terms can really help progress the question.
Yeah, okay, so what you're saying is they told us that this thing compared to L is much smaller than L, and this is much smaller than X. So when I look at the ratio of those two things, I'm expecting something very small, and I could say it's approximately equal to 0. And similarly, delta X over X is approximately equal to 0. And you said about higher powers. So imagine epsilon is a very small number, like 0.1. Then if you square it, it becomes even bigger, 0.01. If you cube it, it becomes even bigger, 0.001. So there are some terms, maybe some higher powers, which we could kind of ignore at some point. So this is a good idea. So these are both really, really good ideas to have when you see something like this. So we haven't even tried, I just want to emphasize, we haven't even tried to kind of answer the question yet. These are just thoughts that are popping into our minds as we're reading the question. Chris, what would you like to add to that?
Well, so just one more thing to mention is on the diagram, they've added this angle theta, and it's not mentioned anywhere in the question, which suggests it's kind of there as a hint or a help. It suggests if we want to use it's just first we might want to use an angle, and if we use an angle, we want to use this angle. Okay,
good. So we've got an angle, and we've got like these kind of approximations. That does remind me of something. Small angles. Daniel, if you could talk about this.
Yeah, so because we see that the deflection is a lot smaller than, let's say, the length of the wire, or x, then I think it's pretty easy to see that the theta will also be a really small angle because the deflection is so tiny. So the the angular displacement, if you know what that means, will be really tiny as well. So this means that theta will be really small. And in that way, we can use small angle approximations, which are really helpful identities to simplify questions. And these include, when you've got really small angles, you have sine theta is approximately theta. And then cos theta is approximately 1 minus a half theta squared. Or depending on how accurate you want to be, you could just say cos theta is approximately 1. Again, depends on how accurate you want to be in the question. And then tan theta at small angles is also approximately theta. So these might help us simplify the question in order to make it easier for ourselves.
Yeah, so if you haven't seen these before, don't worry, it should be coming up in your A-level math syllabus. But basically what we're saying is, if you have a very tiny angle, you can approximate sine theta and tan theta to be theta. You could approximate cos theta to be 1 minus a half theta squared. Or if you wanted to be kind of less accurate, you could say it's approximately equal to 1 as well. If we were ignoring like the squared terms. Somebody asked, what is angular displacement? All it's saying is like, what angle have we turned? What angle have we turned by, basically, is all that means. Yeah. Okay, so that's really good information that we've taken from the first part. And then if we move on, yeah, this would be in radians. That's true. That would be in radians. Now, if we look at part A, Chris, if you could talk us through that.
Okay, so if we just read part A, it says, we're asked to show the small deflection delta x by which the gravitational force Fg between the spheres will deflect them from the vertical is given by delta x is approximately equal to x over 8 minus square root of x over 8 all squared minus lmg over 4x little g. So the big G on the top is Newton's gravitational constant, and the little g on the bottom we were given at the start is acceleration due to gravity, which we now understand means the vertical acceleration due to gravity, the Earth's gravity, because we're now being asked about this extra gravitational force between the spheres. And finally, we're asked to clearly state all assumptions we make and show our workings. So this is 7 marks, and some of our 7 marks are for clearly stating our assumptions and the quality of our working out.
Okay, great. So we will just talk about this G in a second. Somebody's asking about that. But I want to talk about this force Fg for a second. So Giacomo, I don't know if you, what will be your thoughts when you read this, basically?
Well, at this point, we now know what this horizontal force is. It's a force that we would normally neglect because the gravitational force between two small masses is really small. But in fact, that's what the question is focusing on. This deflection is due to gravitational attraction between these two small masses.
So yeah, I just want to, just in case people haven't come across this before. So the idea is that normally we think of gravity as us like being attracted to Earth, but that's only because the Earth is like the biggest or the most massive. I don't know how to say it. The most massive object close to us. So we feel the gravitational attraction from the Earth, but gravitation, like the force of gravity, acts between any two masses. It's just when you see these two masses in real life, you wouldn't. The attraction between them would be so small, you wouldn't normally take them into consideration. So in the chat, somebody wrote, "Oh, can we actually neglect small quantities?" But actually in this question, they don't want us to neglect them and they want us to investigate them. So that's kind of what's happening. So yeah, Giacomo, what would you then, after you figured out what that force is, what would you do?
Well, my instinct would be to start resolving forces horizontally and vertically, because we have this tension force which is at an angle. So we can first resolve vertically. So we know that mg must be equal to t cos theta, because we can draw some triangles there. There we are, like that. And so the vertical component of the tension is equal to t cos theta, that's equal to mg. And horizontally, force Fg will be equal to t sine theta for the same reason. And Fg, we know, is our gravitational force between these two masses.
Yeah, so quickly put in the chat for me, guys. Do you know what the gravitational force between two masses is? And if so, if you could put it in the chat to me, just so I get an idea of how many people have seen this before. And if you haven't, then we can kind of give a little bit more information about it. So If you haven't, just say no, that's absolutely fine. Gives us a good idea. Okay, so quite a lot of people haven't seen it, so I feel a bit bad now giving you this question, apologies. But around, I would say it's about 50-50. Would you guys say? 50% of people have seen it? All right. Yeah, cool. So we're getting half the people giving really good answers, and half people haven't seen it. So essentially, this is the formula. So if you have two masses of mass, say capital M and small m, then the way you work out this force, the gravitational force between them, is there's this constant g, and then you multiply the masses together and you divide by the distance between them. Okay, so in this case, Giacomo, these are our masses. So how would you kind of use this formula?
Well, g is just a constant, so we keep it as g because they want g in the final answer. And our two masses, big M and little m, are actually both just m, because the two masses involved here are the two small masses that are equal to each other.
Oops.
And finally, our r is the distance between the two masses, which is not just x, because x is the distance between the points at which they connect. We need to take into account the small deflection. So it's actually x minus 2 delta x.
Yeah, so we're taking away these ones. So yeah, okay, so this is going to be our FG. So now we can rewrite these equations. What would they become?
They'd become what do you currently see?
Cool. Okay, yeah, so basically this one stays the same. Obviously we can replace our FG with this formula here. So Daniel, now what? I guess it's worth bearing in mind what we're trying to achieve, isn't it?
Yeah, so we're trying to get the deflection that they showed on the bottom, which is delta x is approximately equal to x over 8 minus this term in the square root sign. So I've noticed that there's no theta and there's no tension in there, even though we've got those in our equation. So we've got t cos theta is mg, and then t sine theta is the gravitational force term. So I think we're going to have to get rid of these to hopefully get to an answer that looks like that. So in mechanics, usually you might take away equations, but I think in this one, to get rid of, let's say t at least, we could divide the two equations. And then once you divide those two equations, then you get a tan theta from sine theta over cos theta. And then that's equal to the term on the right. So that's okay. So we've got rid of t so far, but we still have theta, which, as I mentioned, is not in the square root sign or anywhere near that delta x.
Yeah,
so,
there is something I noticed, that there is actually another letter in here which we don't have so far.
Yeah, there's a capital L. So we have to somehow get the length of the wire inside here, even though we haven't got it anywhere around here. So because we've got a tan theta, we might think, oh, it's a trig function. So trig functions are usually related to triangles. And so if we could maybe try and draw a triangle somewhere using that angle, then we could maybe try and get tan theta as an expression. So I think there's a triangle with the wire with length L, and then the delta x is a deflection there. So using GCSE knowledge, I think tan theta is opposite over adjacent. So we've got the opposite, and we've got the hypotenuse actually, but we haven't got the adjacent. So we could try and work this out, but then we get some complicated Pythagoras, I think, which you'd get a square root of L squared minus something. So we need to remind ourselves that the angle we're using is quite small. So at these small angles, tan theta is approximately theta, but so is sine theta actually. So in this small angle approximation, we could use tan theta is approximately sine theta. And this way we can use the opposite and the hypotenuse without having to really work out the adjacent.
Right, so what you're saying is normally it would be O over A, but because we're dealing with small angles and both sine theta and tan theta can be approximated by theta, we could just put them equal to each other. And instead of tan theta, I can replace it with sine theta, which is delta x over L. Yeah,
exactly. And then you get an L term in there. So that's how we should get the L term in the final answer.
Okay, nice. So what happens here?
So yeah, now we can substitute that value of tan theta, which is approximately sine theta, as delta x over L. And then now we can make good progress in getting to the final answer.
Okay, fantastic. So let's move on to the next slide then. So this is the last line that we wrote down. Chris, where would you go from here?
So I think it's worth saying here, we're maybe past the planning stage, and we're just going to show you how we might finish this question, just so you've seen the solution if you were working on it as well.
Exactly. So yeah, so just to emphasize, like everything we did here, really, we were planning what to do, and now we're actually going to do some of the working, just so you can see how we would go about this question.
Okay, so we've got this delta x on the left, which is good. So if we go ahead to what we want to show, we want delta x as the subject. But unfortunately, in our line at the top, we've got delta x on both sides. So we need to do a bit of rearranging before we can make it the subject. If we just think ahead again to what we're going to do, if we look at what we want to show, I think someone said this in the chat earlier, it does look a bit like what you get from the quadratic formula, because we've got some term minus something in the square root, and the something in the square root is something squared minus something else. So it looks a bit like b squared minus 4ac, maybe, if our a and b and c are chosen right. So okay, let's aim to get a quadratic and then use the formula, and hopefully that will work. So if we go back up to the top, if we want to make delta x the subject, firstly, let's get rid of the fractions. So we'll just cross multiply.
Yeah, and that's actually really nice, because now I see the LMG, and I'm thinking that could work out quite well for me.
Yeah, so one thing to watch when you're doing your calculations is look, if you're working towards a particular answer, see if you can get the individual parts of the answer together. So we've got our LMG. And okay, we're aiming to make delta x the subject. So let's just multiply out the left-hand side. So it's all in delta x's. And if we do that, then
oh, sorry. Yeah.
Our first term is, we've got this gx squared times delta x. And then we've got a minus 4gx times delta x squared. And then we've got a plus 4g delta x cubed. Because we had this delta x outside the bracket, and then we had a delta x inside, which was squared. So we get a delta x cubed term. And that initially looks like an issue, because we said we wanted to get a quadratic, and we got a cubic. But okay, there's kind of two things that suggest what we might want to do next. The first is, if we look at what we want to show, we said we've got our LMG, but in the answer, the LMG is all over 4x little g. So maybe we would want to divide by 4x little g in order to get the term looking like that. And there's another reason that's a good thing to do, which is, well, there's actually two. One thing, it gets rid of, it just gets the delta x squared term on its own. But also it would, in one of the terms, we'll get a delta x over x. And that's good because so far we've used delta x over L being very small, but we haven't used delta x over x being very small. And that's something we were told, so it must be useful. Well, actually in the PAT, sometimes they throw in red herrings, but it's probably useful. So yeah, here if we divide by 4x little g, we get this line. And we've written, on the left-hand side, you can see we've written the third term as delta x over x times delta x.
Someone's saying they're confused. I'm just going to reiterate what's happened, if that's okay. So I think people hopefully should be happy with this. We got it from the previous page. We divided the two equations, and we swapped tan theta with delta x over L. Then we times it up by this, and we expanded it out. And we've expanded the whole thing out. Like we just opened up the bracket and kind of squared. We opened up the bracket and multiplied everything through by g delta x, and we got LMG. Now, Chris is saying he saw that in the thing I want, I've got an LMG over 4xg. And also there's a 4xg here, so it kind of makes sense to divide by it. So let's just divide everything by 4xg, and then we get to this line. Okay, so this is where we are now. Oh, and actually, I noticed that one of my delta x's with the x that I just divided by, I could just take that out and I get a delta x over x times delta x squared. But if we remember back to where we were before, we already said that delta x over x was very small, or is close to 0. So we could actually have that whole term kind of be ignored because it's like negligible, it's really small. So carry on, Chris.
Yeah, well, as you said, we were saying if something's very small, maybe we can ignore it. So let's get rid of that term. So we can do that because we're only looking for an approximation. And it makes sense because we said we want to get to a quadratic, and that term had delta x cubed in it. It had 3 lots of delta x, and we only want delta x squared. So now we've got rid of that. If we just rewrite that line again, now we have basically a quadratic. It just needs rearranging a bit. So if we just put all the terms on one side, then we get this, which is a quadratic where the variable is delta x. So we've got delta x squared minus x over 4 times delta x plus ln big G over 4x little g. And this is a quadratic where we've basically got a, if we think about it in the form ax squared plus bx plus c, we've got a equals 1, b equals minus x over 4, and c equals ln big G over 4x little g. And hopefully, if we put it in the quadratic formula, we will be able to rearrange to what we want to get, which does in fact work out. You can rearrange it to that form. The one thing we need to take note of is in the answer we were told to get to, there's a minus. It's x over 8 minus the square root. But when we use the quadratic formula, we don't just have a minus, we have a plus or minus.
Yeah, so I'd like to ask the students, why do we think that we take the minus sign instead of the plus sign, or instead of both of the signs? So yeah, could I get you guys to tell me in the chat why you think we take the minus sign? Just wait for a few more answers to come through. Okay, so a lot of people are saying because delta x is negligible, because delta x is very small. Yeah, that's basically it. So go on, Chris.
Yeah, so it's not quite so much that delta x itself has to be very small, but it has to be very small compared to x. So yeah, what really matters is the ratio between delta x and x. But if we had the plus, so if it was x over 8 plus something, then delta x would be bigger than x over 8. So it's at least 1/8 of x. And you might think, well, okay, 1/8 is kind of a small number, but if we're told delta x is much less than x, they mean less than 1/8. So it ought to be something that if you started writing out the decimal expansion, it wouldn't show up until a long way down. So 1/8 isn't small enough. So that means we need to make delta x smaller, which means we don't have the x over 8 plus something. We must want the x over 8 minus something.
Great. Okay, so that wasn't even the end of the question. We do have a part 2, which we will quickly look at now. So Chris, if you could just quickly talk us through it.
Okay, so if we just read part B, it says, now the spheres are both electrically charged. They have the same positive charge, big Q. How big must big Q be for the wires to hang vertically again? And the hint we're given is we're told the formula for the electrostatic force between two charges is K times Q1 times Q2 over R squared, where Q1 and Q2 are the charges, K is a constant, and R is the distance between them. So the reason they give this as a hint is this isn't on the syllabus, and this time around they decided to stick to the syllabus. But they can give you extra stuff outside if they tell you what it is in the question, as they've done here. What we're being asked to do is find Q that will make the two masses hang vertically. So we might at first think, well, okay, why will they hang vertically again if we make both the masses positively charged? What's the explanation of that? So I think we should try and visualize what the forces will look like in order to make it hang vertically. So in that case, we'll still have the weight acting down, and we'll have the tension acting up, and we have this small gravitational force between the masses. So if it's going to hang vertically and be in equilibrium again, a at the moment in this picture, it's not balanced because there's this force acting to the left. So, okay, we need a force acting to the right, and that must be what's supplied by the electrostatic force, which makes sense because like charges repel. So if they're both positively charged, they'll push each other away. So what we're being asked to do is to make those horizontal forces balance, and that should give us an equation that we can solve for Q. It's worth noting this last part is only 2 marks. So actually it's not the most difficult part of the question. It's just kind of an extension to, I don't know, make it long enough for the paper.
Great. Okay. Thank you so much for that. We actually have one other question that we're going to be looking at. So this is the graph sketching question, guys. So when you were problem planning this in your own time, could you please let me know what were the thoughts that came into your head when you were sketching this? Now, I feel like maybe we should, I'm just going to go back a little bit so you can't see what I've got on the page. But people are writing to me, asymptotes, reciprocal graphs, a lot of people saying asymptotes, turning points, my graphical calculator, lol, completing the square, x and y intercepts, factorization, what happens when x is 0, quotient rule, stationary points, asymptotes, negative values, x increases towards 0, differentiate and put in x values, asymptotes, L'Hopital's rule, hidden quadratic, fractions, and so on and so forth. Partial fractions, somebody said. Fun, yay. Behavior at infinity, like that, yeah. Where x and y tend to infinity and when x and y tend to 0. Perfect. Okay. Yeah, these are all really good. And as you can see, I kind of gave it away because I showed it to you. But I hope, you know, what you guys talked about was very much what we kind of discussed here. Someone asked what's the answer to the last question. Well, maybe that can be an exercise for yourself. It's not the hardest part, and we're doing more problem planning rather than going through the question. We were just nice for part A and we actually went through it. So yeah, Chris, how would you tackle this question?
Yeah, so there's a series of steps you should go through when you're sketching, and then normally in this kind of order, obviously there can be exceptions based on the equation, but normally you want to go through them in roughly the order we've put them. So we tend to start off with the intercepts. So if I draw some axes, where would we get intercepts from? It's useful to remember if we have, so our function here is a fraction, it's 1 minus x squared on the top, and on the bottom x squared. And when you have a function that's a fraction, the x-intercepts come from the top because they come when y is 0, and to make y 0, the top needs to be 0. So what we're basically doing is solving this quadratic on the top, and it turns out to have 2 roots which have some surds in them, but what really matters is one of them's between -1 and -2, and the other one's between 0 and 1. So that's our x-intercepts. And then we might think, well, let's try and find some y-intercepts, which means setting x equals 0. But actually, if we do that, it doesn't work because we've made the bottom of our fraction 0. So what does that mean? Well, it means x equals 0 is actually a vertical asymptote. And there aren't any y-intercepts. So then we think, well, okay, now we're onto the asymptotes. So let's just think, are there any more asymptotes? And there's 2 places to, well, there's 2 kinds of asymptotes we might, even more than that sometimes. There can be multiple asymptotes, but let's start with vertical ones. So vertical ones will come from the bottom of the fraction being 0. The roots came from the top being 0. The vertical asymptotes come from the bottom being 0. But there's only one place that happens, which is x equals 0, which we already found. That's the y-axis. But there can also be horizontal asymptotes, which come from the sort of long-term behavior of the function. What happens when x becomes very big or very small? And the easiest way to find these, at least in this case, is to rewrite the function. Because as it stands, if x becomes very large, the top and bottom both become very large because they've both got x squareds in. Okay, the top actually becomes very negative, but its size is very large. So to deal with that issue, what we can do is just divide through by the x squared and split it into multiple terms, because then some of them might go away. And in fact, that's what happens. So if we just divide through by x squared, we get 1 over x squared minus x over x squared, which is just 1 over x, minus x squared over x squared, which is just 1. And then now let's think what happens when x becomes very large. The first two terms are going to go to 0, and y will approach minus 1. And that happens whether x becomes very positive, so x is going to plus infinity, or if x becomes very negative, so x is going to minus infinity. So there's going to be a horizontal asymptote at y equals minus 1, which we can put on the graph. And all these things are things that you actually tend to get marks for in the question, but they also help you sketch the rest of the curve, which is why it's good to start with them. Because now we've kind of constrained how the rest of the curve can be, because it's got to go through these routes, and it's got to approach these asymptotes. So there's one more thing which you tend to get marks for, which is turning points, which a lot of people mentioned in the chat. So we've now got two forms. We've now written y in two different ways. We've got two forms of the function. And when we find turning points, we normally differentiate. So which of these is going to be easier to differentiate? Well, it's going to be the second one, because it's just a sum of 3 terms, and each of them is basically x to a power. Because remember, 1 over x squared is x to the minus 2, and 1 over x is x to the minus 1. So we can just use our rules for differentiating x to a power. And we won't do all the algebra, because we're just sort of thinking through the steps, like planning the route in which we'll do the problem. But if we did that, we would find there's a turning point at x equals 2 and y equals minus 5/4. But what matters is there is one, and it's also below the horizontal asymptote, which tells us a bit more about the shape. So actually, this question is kind of, you're sometimes alternating planning and doing, because, okay, you have to do some calculations, but now you've put it on some more points. You can plan how you're going to sketch the rest of the curve. So we know that the curve has to go through those two routes, those two x-intercepts. We know it's got to approach both the asymptotes, and it's got to go through the turning point. And we don't want to add any more x-intercepts or turning points or y-intercepts by drawing the curve wrong, because we know we've found all of them. So there's only really one way of joining the dots, so to speak, which is the shape that should come up just now, like this. So it's got to come up from the horizontal asymptote, go through the x-intercept, go up to the vertical asymptote, and then on the right-hand side, it's got to come down from the vertical asymptote, go through the route, go down to the turning point, and then up to the horizontal asymptote. So you...
Just to butt in quickly, for the turning point, we would differentiate and put it equal to 0, but because we're not doing the whole question, we're just planning it, we're just showing you what we would do. And yeah, you would have to do all the calculations for that. So that's how you would find the turning point.
Yeah. So because you know it approaches these particular points, you actually don't need to figure out where it's positive or negative, but sometimes you do need to do that to figure out the shape. So for instance, you could say plug in x equals minus 1 and find the curve is positive there. And that would help you maybe decide where the curve is positive versus negative.
There's just another question about this asymptote. Some people weren't sure where it came from. So I'd just like to add, basically, imagine we get very large, i.e. we keep going along this axis. So x is becoming very large, and therefore 1 over x and 1 over x squared become very, very small. So the graph approaches minus 1, which is this line here. And the same when you go to minus infinity. Some people are asking, well, how can you cross an asymptote? I thought that wasn't the point. Well, this is only an asymptote at like large values of x. It's not an asymptote for small values of x. So that's why that's the case. Sorry,
it comes back up to it. So for instance, I didn't check that the turning point is a minimum, because we don't need to, because we know it just came down from the route on the right hand side there, and it's also got to go back up to the asymptote, so it must be a minimum turning point. So there's often lots of features of a graph you can figure out like that without doing more calculation. And just a few more things. So in case you didn't have enough information from the routes and the asymptotes, you can sometimes figure out, okay, is it positive or negative at this point? Is it increasing or decreasing at this point? And then that will help you sketch the curve as well. A couple of things that don't apply so much to this curve, but would to a lot of others. One is what I described as shape. And one example of that is is the curve increasing at an increasing rate or at a decreasing rate? So just to give an example, if we imagine, say, y equals x squared or y equals e to the x, those curves are increasing at an increasing rate. They're getting steeper and steeper. Whereas if you imagine y equals square root of x or y equals log x, those curves are increasing at a decreasing rate. They're getting less steep, even though they're still increasing.
So you could think of that as like concave and convex curves.
Yeah,
exactly. As well, if you've seen that, or you'll definitely learn about that at school. Yeah, and then symmetries.
Yeah, so some curves have symmetry, and if they do, there will likely be marks for showing that, or it's useful to figure out the shape of the curve to remember its symmetries. In this case, it's quite asymmetric, so it doesn't really apply, but it is useful in lots of questions.
Someone's just asking how many marks this would be. It would actually be, this one is 6 marks in the PAT. Okay, great. Thank you very much, Chris, for taking us through that planning. So we looked at P, which was the problem planning. Again, we did go through some working because we thought we'd be nice to you, and it was a really hard question. But essentially, it was all that stuff at the beginning where we were thinking, where we were brainstorming the small angle formulas and the putting our forces on the diagram. That's all part of problem planning, okay? With reflective reflex, it's what you do after you've answered the question. So you can get a lot out of the question by doing it. But if you think about what you've done after you've done it, and maybe even try and extend the question and try to do the bits that you've made up, you can get a lot more. You can squeeze a lot more out of one question. And there aren't that many questions you can find of the right level. So if you can do this exercise, you can get probably double the amount out of every question that you do. So what we want to ask ourselves is, what did I learn? What was it about the question that made the method I used work? What have I learned here that I could actually use in another question? What if I had to make up a part C to this question, what would it be? Like what potential part C's could I make? If I change the question in a certain way, what works and what breaks? Like what still works and what now doesn't work? So let's do problem planning let's do the reflective reflex for this particular question. I can't remember who was going to go first. Chris, was it you that were going to share your thoughts first on this one?
Yeah, I think so. So I was just going to start with, okay, what's the first thing you do when you're reflecting? Just think in the most literal sense, what did we actually do? Well, so what we did in part A is we found an approximate value for delta x in this kind of situation. And we found a formula for that effectively. It's worth saying here, so you could, if you wanted, rearrange this formula and make something else the subject. So particularly, you could make big G the subject. Someone mentioned in the chat, is this the Cavendish experiment? Kind of, it's much simpler, but yeah, so it's related to a historical experiment that was done to find big G by measuring something similar to the deflection in this question. So although delta x is the subject here, you could rearrange it. And then in part B, we found, or we would have found, an expression for Q. So that would effectively be, okay, what size charge Q do you need in order to counteract the force due to a mass m?
Sorry. Okay, brilliant. So yeah, so this is kind of summarizing what the question was all about. Now, Daniel, if you had to put an extra part to this question, what would your part C look like and why?
Yeah, so I think because of part B, I noticed that they tried to get the masses back to hang vertically again, but they used an electrostatic force, so they repelled them. So another one, using a force that we might be used to in school, we could maybe try and put a spring in between them with a certain natural length and certain spring constant, and then we could try and see what kind of spring we'd need in order to push these back so that they hang like they were before. So instead of using the repulsion, use a spring to push them back out and see what values we can get.
Okay, so maybe see like how stiff the spring would have to be in order to get it to the to get it back to its vertical position. Okay, that's really interesting. Yeah, Chris, what about you? Did you have any other thoughts on how we could extend the question?
Well, one way to extend the question is to think, okay, what was nice about this question that made the method work, and then try and break it and see if the method breaks down and what else you might need to do instead. So one thing that was nice about this question was it was very symmetric. The two masses are the same. So what happens if we make one of the masses bigger? So if we have, say, m and 2m as our masses, how would the question change? What else would we need to do? So yeah, it might be worth trying that and see like what still works, what goes wrong, whether you could use anything else in addition to what we did in this question.
Okay, Giacomo, what about you?
Yeah, well, I mean, an interesting thing I thought was that these small angle approximations, people doing A-level currently probably aren't really very familiar with them because they're not used that much in school. But actually, they become second nature once you're starting a physics course. They become really very common. And so this reminds me of what I said earlier about the PAT mimicking university studies and testing you and preparing you for what you're going to have to get used to later.
Yeah, exactly. Why are approximations used so much at university?
Well, because in situations like this where you have pendular things swinging about, basically any mechanics situation, where you'll start modeling it using differential equations. And differential equations get very complicated very quickly if you have sort of higher order terms. And so what's often useful is to cancel those higher order terms using approximations, whether it's small angle approximations or binomial or the Taylor series. And so they come very frequently in order to simplify these complicated differentials.
Okay, great. That's really helpful. So yeah, as you can see, this is how you'd reflect on the question, like, what did I learn from it? What did I take away? How could I extend the question and actually go and do those questions and see what happens? And yeah, I think that's really interesting. What about here, Chris? What would you take away from this question?
Well, so what did we do? We sketched this function. So is there anything else that we've maybe learned that we could apply to other types of question? What other types of question might we now attempt in order to extend this? Well, what's the form of the function we sketched? It's basically a quadratic over a quadratic. So one of my first thoughts might be, well, what if I use different quadratics on the top and the bottom? Especially on the bottom, because at the moment it's quite simple. It's just x squared. If I make that more complicated, how does the graph change? And also, we saw that we got asymptotes and intercepts from the roots of the quadratics. So what happens if we change the number of roots on the top or on the bottom? And then further than that, okay, what if we move away from quadratics? So what if we have a cubic and a quadratic, or two cubics? What happens then?
Okay, yeah, that's really interesting. You can also use other types of. Someone's asking, is this graph a function? I thought it wasn't, as not all values of x map to a value of y. Well, okay, just as an aside, well, you could just take 0 out of the domain, and then all the values in your domain do map to somewhere else. So that's, yeah, it's a really interesting point. But yeah, you can look at different types of, I just want to emphasize that these same points, x-intercepts, y-intercepts, asymptotes, turning points, are used for all graph sketches, no matter if it's got just polynomials or if it's got sines, causes, learn anything, you will always be looking at these points. Giacomo.
Sorry, I was just replying to the function question. One other thing that I think is worth mentioning here is that if you enjoy graph sketching, then you're in luck, because you're going to keep doing it once you get into university. I've still got plenty of these questions to do, and it's interesting to know I do these exact steps every time. So it's really worth internalizing them, because they will keep being useful.
And especially in your Oxbridge interviews and Oxbridge exams, it's really worth knowing. It's something that is not covered that much at school or in the A-level syllabus. Okay, now just to move on then, so we've done problem planning and reflective reflex. Now we're looking at outline and organize. So by this, what we mean is laying your work out well, laying it out logically. So how do I lay my work out? With clarity, draw good diagrams, have valid reasoning throughout your working, and make sure you don't miss steps out. Like you have a complete set of kind of work. Now, this is for two reasons. Obviously, if you're sitting an exam where the examiner is going to see it, you're doing it partly for the examiner. But even if you're sitting the NSAA, a lot of students say, oh, well, the working isn't really important. It's just a multiple choice test. I don't need to lay my working out well. But one thing I want to really, really stress is, if you want to, if you can write your solution out well, it means that you're thinking about it well. if you can write it with clarity, it means you have clarity when you're thinking about it. So it's almost a product of you thinking well. And that's kind of what we want to get at. And I think training yourself to write things clearly trains you to think about things clearly. Also, when you're in a pressured exam, people think, oh, I'm going to make it really messy and quick because I don't have time. But then if you go wrong, you have nothing to look at to kind of correct your working. If you lay it out quite logically, it means you can go back and correct your work and see where you went wrong much more easily. So it's as like I say, it's not just for the examiner, it's also for you. Let's look at this example. This was somebody working out. This isn't even their working, by the way. I want to emphasize their working for the actual question is beneath this. This was just them setting up their working so that they could have it all in front of them to start the question. Kind of like we did in our mechanics question just now.
Yeah, exactly. So we can see at the top they've drawn a relatively clear, well-labeled diagram of the whole situation. So it's basically a pulleys question. We've actually got 2 pulleys and then a mass hanging in the middle and 2 on some slopes. But because that's quite complicated, because there's 3 masses, and we might care about the forces on each of them, they've then kind of exploded this diagram and zoomed in on each of the masses to draw the full force diagram for each one. And it's often good to split up a diagram like this, because if you try to draw on all the forces on one diagram, it normally gets very cluttered. It gets hard to draw on all the right angles and label it properly. So it's very often a good idea to split it up like this and then draw the individual parts much larger and clearer. It's also worth pointing out that in the middle, we can see they worked out 2 angles. They did this by recognizing some Pythagorean triples, so some sets of integers that make a right-angled triangle. And that would be with information given in the question. But they've marked on those right-angled triangles to show where they got those things from. And then if they maybe got one of the angles wrong, so they got the fraction upside down or something, they could just go back and check the triangle, and they'd know where it came from.
Yeah, and I want to emphasize that they haven't done this they've done it just to clarify their own thinking, and it's going to help them in the rest of the question. So, the other thing I was going to say is I don't know what the original question was, but I have a pretty good idea just from looking at this person's working what the question is asking. So there's just a number of, I know the setup of the question, there's just a number of things that could be asked as the next steps, but yeah, I've got a good idea of what this person was trying to achieve. Here, this is a question from an NSAA paper. So this is from a multiple choice paper. And even though it was from a multiple choice paper, this person has laid all their work out clearly. They've said what variables they've given their variables names like I0 and I1. They've kind of laid all their working out nicely. They've created an equation and then they've worked their answer out. So it's it's done in proper equations. It's not guessing. They haven't kind of made up what they're doing. They haven't just written a few things down. It's in a really logical format. Chris, I don't know if you want to add anything.
Well, just that they've started with a diagram again, and they've clearly worked out and labeled the 2 currents they're finding. Which they can then use to solve the equation. So we can see they've done this very quickly, but also very clearly.
Yeah.
I think Giacomo had one comment on how the PAT is used and why that's relevant to outlining your work clearly.
Yeah, so I've actually spoken to one of my tutors about this, and he gets very frustrated marking these PATs because I have a lot of them to mark. And what's really frustrating for him is the sort of neatness of it. Bear in mind, they have your PAT script while you're at interview, and the people who interview you will most likely be then teaching you. And they don't like marking unneat work. So you want to put your best foot forward and really show them that you'll be a student that they will want to teach. And so that's another argument for laying it out nicely.
Yeah, exactly. And as a former teacher, I know that I found it really frustrating to have to trawl through all this really messy work and illogical work where I couldn't figure out what they were trying to do. So I can completely sympathize with them or empathize with those examiners and interviewers who are having to read through all of this work, yeah, do make it easy for them to let you in. Okay, so give them an opportunity to like what you're doing. All right, so let's move on then. So the last thing we're going to look at is the F in the PROF methodology, so fast and fluent. So as we said already, you've got to be quick in these exams, and especially for the NSAA, being quick is really the name of the game. Like, it's testing your speed and fluency with concepts. So the way you can kind of do this is with time practice, but also there are a number of little tricks that you can learn that will help your calculations become faster. And Giacomo actually mentioned we have one of our courses is literally called like Physics and Maths Time Saving Tricks, and that was one of the courses that Giacomo attended. So we literally give you these little tricks that you can make your, you know, that might give you like 3 or 4 extra seconds per question, but that might mean that you can do 2 extra whole questions, whereas you might have had to leave them otherwise. So I should also emphasize that becoming fast and fluent is a natural consequence of the P, R, and O part of this. So let's go forward then. Chris, if you could just talk us through and explain. I mean, look, guys, we don't want you to read the question because it's quite long, but there's just a mini trick in there that you can apply, and Chris is going to go through it.
Yeah, so this circuit's just part of a longer question, but we have a circuit here with these 4 identical resistors, which are rectangles, and then A, B, and C, which are also identical components, and they all have the same resistance. And the circuit has a voltage of 84 volts across it. In case you haven't seen these symbols before, the symbol on the right-hand side just means it's held at 0 volts. And on the left-hand side, that end of the wire is held at 84 volts. It's like there's an 84-volt cell across it. So as it stands, it's a complicated-looking circuit because there's multiple paths around it. You can't easily split it up into just some bits in series and some bits in parallel like you might at A level. But there is a trick to make it simpler. Maybe
we can ask people in the chat. Can anyone see what the trick is? Let's just see if anyone comes up with it. What trick can you see that could simplify this circuit? Someone's saying Kirchhoff's laws, maybe loops, symmetry, expand it out, equivalent resistances, redraw it, split it, symmetry, redraw, map a diagram, loops in the NF, drawing a diagram, redrawing, equal drops across resistances, laws of equivalent exchange, look for shorts, Kirchhoff's laws, getting that a lot. Right, Chris, what would you say is the trick here?
You can use Kirchhoff's laws and break it into loops, but that's kind of the long way of doing it. So it does work, but it means you need to write down a bunch of stuff. The sort of short trick is if we just look at this component A and look at the 2 ends of that, the top end is halfway between these 2 identical rectangular resistors, and the bottom end is halfway between the identical components B and C. So if we think about what the potential is at each end of that wire, they're actually the same. They've both got to be 42 volts, basically by symmetry, because the circuit's symmetric down the middle. So it basically has to be half of the potential in the middle. And if the potential at each end of the wire is the same, then there's no potential difference along that wire. There's no current flowing through it. So firstly, we know, okay, the potential across A is 0, the potential difference. But that lets us do one more thing to help us simplify the circuit. So now we know there's no potential difference across this wire. There's one more step we can do, which is we could just take A out. It's not making any difference. If the 2 ends are at the same potential, it doesn't matter what's in between them. It won't affect the rest of the circuit. So we can just get rid of it. And once we do, it's much simpler because now we just have 3 branches in parallel, each of which is made of 2 identical components. And so we simplified the circuit a lot for ourselves. And you could just do that in 5 seconds.
Okay, great. Let's have a look at another one.
Yeah, so this one, we have a pendulum, and we know we've got a string of length 50 centimeters, and the distance from the edge to the middle is 30 centimeters. And we're asked to find the speed it has in the middle. This is, well, there's something we should recognize about the numbers in this question.
Okay, do we have it in the chat again? What does anyone recognize anything nice about the numbers that could help us? Yeah, everyone's saying Pythagoras. Yeah, exactly. Yeah.
James saying it is cheating. He's already on the program.
Who's on the program?
James.
All right.
I can see you. You can't hide. Yeah. So lots of people are saying it's a 3, 4, 5 triangle, which is right. So if we fill in the other sides of the triangle we're talking about, we can immediately read off this height is 40, and that means that the bob, the mass on the pendulum, has fallen 10 centimeters between the edge and the middle. And that would allow us to find the speed using conservation of energy.
Yeah, so that was an easy one, 3, 4, 5. I think it's worth kind of knowing and remembering other Pythagorean triples, as that student did in that work that we saw. They really can help speed your working up. Let's look at this then quickly. So Chris, if you could quickly, so that we don't have to read it, just quickly explain what's happening.
So the bit we're interested in is actually just the last line. Does the rate of change increase or decrease with time? Well, we do have to know what rate of change it's talking about. It's saying we've got a cylinder, the height is changing in a linear way. So it's like the original height minus some multiple of the time. And we want to ask the question to find the rate of change of the radius. So what you could do is you'd have to calculate the rate of change of the radius anyway, and then you could find the second derivative and ask, is it positive or negative? But you have to do a bunch of working out, and it's a bit messy, as shown.
Very messy.
One of those questions where they go a bit beyond the syllabus. So you might not technically know how to differentiate when you've got this h minus alpha t inside. So what's another way of doing this? You could actually use your physical intuition to figure out whether the rate that the radius is increasing with will the radius increase at an increasing rate or a decreasing rate? So if you just physically think about what's going on.
I don't think I can actually play this video.
Okay.
I might be able to, but right. Why don't we carry on talking about it? We play at the end.
Okay. Yeah.
Okay, stay till the end if you want to see what happens in this cylinder. Okay.
But yeah, the point is, if you imagine squashing this cylinder, the height will reach 0 in a finite amount of time, and because the volume is fixed, if the height goes to 0, the radius has to go to infinity. So the radius is going to go to infinity in a finite amount of time, as if it's approaching a vertical asymptote. If you imagine the graph of the radius against time, it's just going to blow up to infinity. And that means it has to be increasing at an increasing rate. Otherwise, it wouldn't be able to approach the asymptote like that.
Okay, that might have made more sense if you saw the video, but we will play it at the end for you, so do stay tuned for that. Hold on. One sec. Is this going to play now? No, sorry about this. Okay, then the last one. So the long way of doing this question, where you have to find the coefficient of x cubed in this expansion, would be literally to do the fifth power everything with binomial expansion and then try and find what the x cubed term was and find out that it was 0 and all that working. But obviously the quick way is to do what? Who can put it in the chat for me? What's the quick way of figuring out the coefficient of x cubed there? Yeah. Okay, a lot of people are saying it. I'll just wait for a couple more people to say it. So basically, yeah, it's the difference of two squares. If you actually multiply the brackets first, you actually end up with 1 minus 4x squared to the power of 5. And in this, all of the powers are even. So whenever you do it to any power, you're always going to get even powers, which means the coefficient of x cubed is going to be 0. Okay, so yeah, that is those are just some examples of like little tricks that you can use. There are lots and lots more that we teach in our course. So lastly, exam technique. So I'm going to go through this quite fast. So obviously we've said problem planning, identifying key info and starting points, and annotating a good diagrams. The other thing is timing. So I don't know if either of you want to talk about timing in your respective exams. Daniel, maybe you start.
Yeah, so as I'm at Cambridge, I did the ENSAA in its first year, and the format meant that that it's really time constrained, as was mentioned earlier. So you have to think about you have to essentially save time at the very beginning when the questions are quite easy, in order to give yourself a lot of time later on when the questions do get progressively harder. So as I said, you're not expected to finish most of them. So a good technique is to try and get all the questions you can do quite easily. And then the rest of them, you might have to do a bit of educated guessing, depending on the kind of variables they give or different quantities they might give. And then also...
Sorry, I was going to say, you are expected to try and do as many as possible. You should be expected to do most of them, but you might not finish all of them. So yeah, and so at the end, what you're saying is you would make some educated guesses?
Yeah, exactly. Because there's sometimes there's quantities in there that might make it easy to see what the answer could be like. And as you get more persuasive, then you might be able to eliminate a lot of them based on a bit of intuition, essentially. But some you might just have to guess if you really do run out of time. But hopefully you won't need it.
So yeah, this is the last few minutes. You might want to make some educated guesses. In general, there are normally so many options that elimination, I don't think, is the best way to do these questions. Giacomo, I don't know if you have anything to add.
Not really. I mean, the PAT I found quite time pressured as well. The thing about the PAT is it's often quite easy to know what topic each question is referring to, because there's very often a diagram there, or often within the first few words you sort of understand, okay, it's referring to circular motion. So you can quickly see whether it's a topic you're strong in or weak in.
Okay, great. Yeah, so assessing the questions, and maybe if it's something you're weaker at, skipping it and then coming back to it at the end. Okay. So yeah, some other tips for timing would be to draw a diagram as you're reading it. So don't read the whole question and then draw the diagram. Do this as kind of we did with our with the pendulum question, not the pendulum, but with the masses on the wires question. We were putting the forces on as we were reading the question. That's kind of what you want to be doing. Try and keep all your algebra. So you want to keep all the letters in there until the very end and only sub in numbers at the end. That will save you time because you might see things that cancel. You might want to even keep factors. So instead of writing 256, you might just keep it as 16 squared, because then you might notice things cancelling as well. Remember all versions of equations. For example, here's an example. I think, is this in a spring? Energy is F times force times extension. And the other version of that is energy is half times the stiffness times the extension squared. So if you know both forms, you'll be able to find the quickest one to use in that particular one. And then guessing multiple choice answers at the end, as we just already discussed. And then also using the size, if you know roughly how big something should be, the order of magnitude of what the answer should be, you can sometimes cross out ones which are too big or too small. You can look at units, and then you can even check using by subbing in special values and seeing if those work. And lastly, educated guessing if you're really kind of low on time. And also your non-calculator skills should be sharp. You should know all your trig values off by heart. Anything that you're used to doing with a calculator that your teachers probably told you, it's best if you learn that off by heart. Honestly, it is better if you learn that off by heart. So trig values is a big one that springs to mind from what I remember people never wanting to learn. Special triangles, Pythagorean triples, formulas. You don't get a formula booklet, so it's really important that you do learn things off by heart.
Oh, can I just mention arithmetic? Being good at your arithmetic really does save you time, because if you have to spend a long time just working out the values, it can eat up a lot.
Yeah, so knowing squares, cubes, your prime numbers, knowing powers of 2, I think could all be really, really helpful in something like this, off by heart, so you're not having to calculate them. Right, so what should you do between now and November to maximize your score? Well, start now. I mean, there is the longer you give yourself, the more you'll get an opportunity to improve your problem solving skills. And you can do it a little bit by bit by bit. you'll probably see when you're solving a problem, sometimes like you're solving a hard problem and then you wake up the next day and you've got a solution because your brain's kind of processed it. The longer you give yourself, the more time you're giving your brain for that processing to happen, instead of kind of cramming it all at the end. I definitely say start early. By the way, guys, I know we're a little bit short on time, so I'm going to kind of rush through these points, but if you want to add anything, feel free. Past papers, do as many as you can. Now, there are lots of past papers for the PAT. There aren't so many for the NSAA. So what can you do if you, because there aren't enough past papers? Well, you can look at other tests. So ENGAA and NSAA share quite a lot of the same questions, but ENGAA adopted the new format of section 2 years ago, whereas NSAA only adopted it recently. So you can look at ENGAA for extra questions. Obviously, the MAT, which is the maths exam for Oxford, that has multiple choice maths questions, which you can use to practice. If you're doing the PAT, do the NSAA, and if you're doing the NSAA, do the PAT. They will both be really useful, not only for the test, but also for the interviews. So I strongly recommend that. And if you sign up with us, we have a whole bunch of videos. And when you sign up for, say, the NSAA, you get access to videos in all of these different areas, plus lots of other questions that we've made up. So these are really, really good sources. It's quite difficult to find questions of the right level. You want to generally be improving your problem solving skills. As Giacomo said, don't stick to this narrow syllabus. Get yourself into this problem solving mindset and actually enjoy it. It's really fun. So Olympiads, challenges, finding problems elsewhere, just get yourself out of what you're normally doing just with your work at school. But then closer to the time, you want to be doing timed mocks in real exam conditions because you need to see how you perform under the time pressure. So I would actually reserve a few of the papers on both the PAT and the NSAA to do just in like the last month before the exam, so that you're really giving yourself that timed mock practice. If you want other mocks, we do have extra questions that we've got in our online resources. And then we of course said reflecting on previous questions. Sometimes you can see little tricks by reflecting on questions, or you can see why something worked, which will help you apply it to a future situation later. Is there anything that you guys wanted to add to that? Okay, and then just look back and see, was there a more efficient method? You can look at the official solutions, or you can watch some of the videos that we've got in our online resources and see how the tutor did it. Did they use a different method that actually could have sped your working up more? And of course, use the tricks that we teach you. Now let's go through the Q&As, and there are literally, there's 102 of them. So yes, there will be a recording of the webinar for people who registered. So we'll send that over to you in the next 2 or 3 days. Okay, oh, we got quite a few comments, which are where people are from. Oh, someone's from Egypt, wow. Do you have to do the PAT if you're applying for Cambridge? The answer to that is no, only the NSAA. If you get extra time in A-level, will you get extra time in these tests? I believe the answer is yes. However, I'll admit that I'm not an expert, and I think you should check with your examination officer. I'm just going to answer the questions I can quickly, and I'll pass them over to you guys if that's okay. Yeah, okay. For the NSAA, can you pick the same science for section 1 and 2? Absolutely, yes, and I would recommend it. It means you just have to prepare one subject. If you have extra time, yeah, I think, like I just said, yeah, I think so. If I'm applying for physical nat ski and I'm interested in both the chemistry, I'm assuming that person's saying, yeah, the chemistry and the physics. Will the admissions tutor prefer if I did one section in chemistry and one in physics, or should I do both in one? I don't really think it matters. I think you have to kind of choose your preference, and you could do one of each, but I don't think it would matter if you did both in the same subject at all. The slide pack won't be shared, but we'll be sending you a recording of the webinar, so hopefully you'll be able to look at that again if you have any questions. Are there any topics likely to come up that would have been covered in further maths, but a single maths A-level student wouldn't normally have covered? Not really. The topics we mentioned are kind of like astronomy, which isn't really, oh, so that's not even a maths topic, apologies. I don't think there would be any further maths topics in these particular tests. There might be the odd thing, like Giacomo got asked about matrices in his physics interview, and that is something that is a further maths topic. I haven't really heard of that happen much, to be honest. And you can always say, I haven't studied this, and they will take that into consideration. Like, you know how when we looked at the question today where they said hint, FQ equals K Q1 Q2 over R squared, or whatever it was. they actually gave you a formula if you weren't meant to know it. And in the same way, they would give you more hints if you say that you hadn't done a topic before. What is a good grade for the step? 75 to 80% is kind of what you want to be aiming for if you want to seriously have a chance of getting in. For physics and philosophy and joint degrees, do you know if we'll have to sit the NSAA PAT and the philosophy entrance exam? I think the answer is no, but Giacomo can give further information on that, and maybe Chris, because he did maths and philosophy.
Sorry, can you repeat the question? That was very quick.
Sorry. Do you have to sit the philosophy entrance exam if you're doing
No,
physics?
you will have interviews in philosophy, which are a lot of fun, but no test.
Okay.
I think the test is for philosophy and theology only. I could be wrong, but I think it's just that.
I think you have the option of taking it if you're doing philosophy and modern languages.
I see. Okay. Yeah.
Okay, cool. What's the pass rate of the PAT assessment? Now, that's an interesting question. I think it's not really a pass or fail, but I think they interview around 50% of applicants. It's from recollection. That is changing every year. More and more people are applying to Oxbridge. So obviously that reduces the amount of people they can interview. So it would be worth checking what it was in the last year. I don't have last year's data to hand at the moment. What is an impressive step score? So most students who get in will be scoring around the 75 to 80% mark, is what I would say. How different is an engineering degree to a physics degree? Are theoretical topics like particle physics covered in the engineering degree? Who would like to answer that question?
I'm just doing engineering.
Yeah?
No, is the short answer.
Wait, what?
It's no to particle physics.
Okay, no particle physics. The question was, how different is the engineering degree to a physics degree?
The math is very similar because you need all the same maths. You do basically the same. We have this almost identical exam for math methods. It's almost identical. The actual physics, though, if you're doing a physics degree, becomes theoretical pretty quickly, whereas engineering does not.
Okay, all right. So engineering is a little bit more practical, and I understand that there are more like here make something, like make a bridge, that kind of thing. Whereas in physics, I think it's more like experimental theoretical. Would I be right in thinking that?
Yes.
Great. Okay, an average score for the NSAA. So the NSAA is okay, so sorry, let me answer this question first. What exam for engineering at Cambridge? There's a test called the ENGAA, ENGAA. It's actually very, very similar to the NSAA. So it basically has the same questions in a different order. So yeah, it's very relevant. What's the average score for the NSAA? So they do scale the marks for the NSAA. I think it's on a score of like 1.0 to 9.0. And I think the mark you need to get an interview is roughly 6.0. So that's how they scale the marks, but it will depend. They do standardize them depending on the difficulty of the test. Do any other unis use PAT for their application processes? Not that I'm aware of at the moment. Does the book have information on ENGAA? Yes, it does. Who do they offer these assessments to? Is there a way of determining it, or is every candidate given the chance to attempt the exam? Yeah, if you apply, you can sit the exam. There is no kind of entry requirement to sitting the exam. Everybody can sit it if you've applied to the uni. You do have to make sure that your school knows and your examination officer enters you. Will there be any changes to Oxbridge entry requirements due to the effect of COVID in our year? That's a very difficult one for me to answer. Ultimately, everybody has had the same challenges, really. When you say entry requirements, if you mean A-level requirements, I actually don't know what the answer to that is, to be honest. It's probably better to check on the Oxbridge websites to find out the official line. Obviously, it's very different this year, what could happen. In your year, though, for A-levels, I guess everyone has been in a similar position. I know not everyone's been in the same position. People have had different levels of schooling and so on. So one would hope that they would take that into consideration, but there is no guarantee. And I can't say right now what they're going to do, unfortunately. Does the NSAA ever give diagrams in questions? Yes, it does, but often it doesn't. So there are some times when you have to draw your own diagram. Considering that they're looking at your problem solving skills, do examiners look at your working and not just the answer, even if it's for a multiple choice? I think for the multiple choice, really, they don't so much from memory.
For the PAT, you can get 1 out of the 2 marks if you got good working.
Yeah, so that's for the PAT, but for the multiple choice question.
And so no, they don't. They just take it as whatever you put the answer as. So
Okay, so just to stress that PAT also has multiple choice, and they will look at your working there. But NSAA, which is all multiple choice, they don't look at your working there. Are you at a significant disadvantage of getting in if you do maths A level instead of further maths? I think it's just the people who do further maths will be just doing a lot more maths than you, first of all. And then the second thing I would say is when you get to uni, if you're then with people who have done further maths, like what they say is that, you know, you basically do the whole of further maths in like a month, like, you know, it goes very fast. So if you're in that position where you haven't done maths A level, I would say if you can sort of do it in your own time, maybe just look at a few topics over the summer between year 13 and uni, that will really help you as well. You know, if your school doesn't give you the opportunity to do it, obviously they will take that into consideration. But if your school did offer it and you didn't take it, then they might think, why didn't you take it? And I just would like to emphasize that physics is a highly mathematical course. So the more maths you can do, the better it will be for you.
I know someone who applied for natural sciences and was advised by his college to do a lot of the further maths material after he got his offer, but before he went.
Okay.
So yeah, at least some colleges think it's basically necessary.
I mean, I would say the more you can do, the better. Daniel?
Yeah, I just want to mention. So as Chris said, a lot of colleges see it as compulsory, especially in Cambridge. But then my supervisor in first year didn't mention just that you learn more topics in further maths, but it's the style of thinking you're introduced to in further maths as well. But even if you didn't learn all the content, learning different approaches for problems really helps, especially for knowing different ways of attacking problems. So it's a really good to just learn in your own time, as everyone else has been saying.
Okay, great. Yeah. I'm super grateful for all the audience members who are still here. We've still got over 200 people on the call, and I appreciate it's 10 past 10 nearly. So thank you very much for your patience, and hopefully this has been really helpful for you. Obviously, feel free to book a call if you're still interested in finding out more about how we can help you, but there's lots more questions, so let's get on with them. Are all the exams for engineering, physics and maths the same? No, they're quite different. And you can read a lot more about that in our book if you like. Our book is called The Oxbridge Formula, and it's available on Amazon. We'll be giving you a copy of this. Someone says cry. Okay, all right, good. What are the most efficient ways of specifically improving problem solving skills? I think we've covered a lot of that with the PROF, the PROF method. Do we need certain requirements before obtaining a chance to take the test? No, as we said. Hi, is it possible? Okay. Okay. For someone interested in theoretical physics, but not so interested in experimental physics, would applying for maths or physics be a better route? Who would like to answer that?
If you don't like experiments, just physics and philosophy.
Oh,
we have no experiments. It's brilliant.
Okay. Any other suggestions?
Oh yeah, a lot of mathematicians I know picked maths specifically because they didn't want to do experiments, but it's more like the applied modules that they do in physics. So I think maths might be the better option, or physics and philosophy, like Jacobo mentioned.
There is the maths with physics option at Cambridge.
Yeah.
Yeah.
There is a maths with physics option there, and okay, you would, if you took this route, you would have to do experiments. But Oxford has the 4th year, which is like a master's in maths and theoretical physics.
You're going to get that from physics and philosophy as well.
Oh, can you? Okay.
Yeah, you can do physics and philosophy for the first 3 years and then switch to a maths.
Chris, what were you saying?
I think you can get there from any maths or physics degree. It's like
for maths as well.
Together, you can change that in your 4th year.
So if you like theoretical physics, I believe that the Cambridge course is more physics based than the maths than the maths course. Sorry, I believe that the Cambridge maths course is more physicsy than the Oxford maths course. So that might be helpful. All right. Is there much on the Northern Irish spec? I don't know anything about that spec. I'm going to be honest. What I recommend you do is look at the PAT and NSAA specs. They're available on the Cambridge website. I think also if you download a guidebook on our website, if you go to oxbridgeformula.co.uk, which will redirect at the moment to stepmaths.co.uk because that was our old site, and then we have some free resources, and on there you can see the guidebooks, and that it's got kind of syllabus information in there, and you can compare it to your own board. I think that'll be the best thing. Okay. Is it common that we treat lots of variables as negligible in the PAT?
I think they often tell you.
Yeah, I think it's... Go on, Giacomo, sorry.
Well, I mean, the example we looked at, we had the significantly less than sign, and that's a big hint. Alternatively, they will tell you this is negligible, or they will say state your assumptions, at which point it should be quite clear what you're going to have to assume. So it should come quite naturally.
Okay, great. So someone says, if physics is undertaken at university, is it possible to get into an engineering-based occupation? Anyone want to answer this?
The actual engineering degrees give you the qualification to be a chartered engineer, which you wouldn't get from a physics degree. I don't know a lot of physicists who went into engineering, but I'm sure it is possible to, say, work for an engineering company. You wouldn't have the as engineering is a licensed occupation, so you wouldn't have that qualification by your name.
Yeah. Okay. Yes, we'll send you a recording of this in a few days' time. And if there's anybody else you know who would benefit from this webinar, feel free to also send them the link to sign up. Do you offer any programs more related to the natural science, biological natural sciences, or veterinary sciences? We may have something launching later, so watch this space later on this year. So watch this space is what I would say for that one. What is your personal experience of going through this experience? What did you do to prepare, and how much dedication is required? So Daniel, could I get you to answer this first? I'll repeat. What was your personal experience going through the application process? How and what did you do to prepare, and how much dedication was required?
Yeah, so in my experience, because I did the ENGAA, it only just come out with a specimen paper. So in terms of the past paper section, I just had to just do the paper once and see how well I did on it. But also the longer section, which was section 2, the questions were quite a bit more challenging. So I would reread it on YouTube videos how to maybe solve some of those. And in terms of extra preparation, I just made sure to really understand what I'd learned in year 12 and possibly bits of year 13, so that I knew fundamentally about each topic rather than just memorizing them at A level, which is a lot of the times that's what you need. But for the admissions test, I really want to see how deeply you understand topics. So mainly revisiting content was how I prepared, and I think it put me in good stead by the time of the exam.
Excellent. Does anyone else want to give their opinion on that question? Giacomo? I think you've already said, to be fair, I think you've already
quite
said.
A bit.
Yeah, I think you've already said. Okay, that's fine. A question for you, Giacomo. Why did you choose physics and philosophy over just physics?
At the time, I was interested in philosophy. I was doing some reading already, and it was something I enjoyed. A big reason for me was that my physics teacher told me he did a physics degree and he'd basically forgotten how to write. And that didn't sound very appealing because I quite enjoy idea writing. So I wanted to keep that side of my academic life open as well. And that's still really relevant now because essays really break up all the problem sheets. It's really refreshing to have an essay to do it instead of just more maths. And those are the two primary reasons, I think.
Okay, cool. Do we have tutors for chemistry, as we haven't really spoken much about chemistry today? So as part of our program, we specifically focus on the physics part of the physical natural sciences, but we do have chemistry tutors. So if you want one-to-one support from chemistry tutors, we can definitely provide that. If you get, we've done the extra time. If you have specialist interest in a certain field of physics, will you get a chance to talk about them in interview? I don't know if either of the recent interviewees can discuss that.
I did. In my personal statement, I put some stuff on a work placement I'd done in research and development, and we finished the interview not even early. I don't think we had much time, but they were interested, so they prompted me to talk a bit more about that.
Yeah, I just emphasize though, they're not normally judging you. If they're asking like a question which isn't like a problem, they're not normally judging you on it, but they might just be interested to find out more, or that might lead into a problem, which is where they are kind of judging you on how you approach a problem. Daniel, I don't know if you wanted to add anything.
Oh, was this on the interview section about the types of questions?
Yes, if you have any specialist interest in certain fields of physics, will you get a chance to talk about them at interview?
So in my interview, it was a bit different. So I mentioned certain topics on my personal statement, and as mentioned earlier, they don't really care about your personal statement. But the questions they gave me were like technical questions based on things I had put in my personal statement. So I mentioned quantum mechanics, I mentioned black body radiation. So they gave maths/physics questions based on that. They didn't ask me directly, oh, what did you learn about these topics? It was just, yeah, can you do the physics and maths a bit? So yeah, I guess it depends on the interviewers, but that's my experience.
Yeah, I think if you put a topic down, do be prepared to have a problem. Yeah, you could have a problem on that topic. I think it really depends on the interviewer though. So I know some colleges just have set problems, and some might think of problems based on your personal statement. During the interview, what kind of questions should we ask at the end? Now, I actually watched an interview with like an Oxbridge academic who was saying that they're not, like, the question is for your benefit. They're not testing you on that question. And if you don't actually want to know the answer, don't just try and look clever, because they're quite busy and they don't just want extra questions to answer. That was literally the feedback that they gave us. Okay, so somebody asked, what is harder, the ENSA or the PAT? So I think from my knowledge, the ENSA questions themselves are not that hard, but what makes the ENSA difficult is the sheer time pressure. As we've seen today, the PAT questions can become quite difficult. I don't know if anyone wants to add anything onto that.
The PAT's harder.
Yeah, I mean, I would say that my thinking would be the PAT's harder. For the ENSA, you've kind of got to drill yourself to do the questions really quickly. Would you recommend physics and philosophy, and what is it like?
I would. Bear in mind, it's very time consuming. You're doing all the physics that is in the normal physics course, minus lab work and optics and circuitry. So you remove the stuff physicists don't like. The majority of people complain about exactly that: lab work, optics, and circuitry. But in place of that takes up not too many hours a week. You've got extra problem sheets for logic and an essay a week to do, and that takes up a lot of time. You've got a lot of reading for that, etc. So be prepared to spend more. It's one of the most time-consuming degrees. I still think it's worth it. As I said, the essay writing and the reading is a really pleasant break from just the hard maths. It's also a bit broader. You sort of analyze. You do a lot of philosophy of physics. It's quite specific to Oxford, but there are specific philosophy of physics tutors. So a lot of the modules I do are the philosophy of space-time, philosophy of relativity, philosophy of quantum mechanics, and they're all they add a dimension to physics that normal physicists aren't doing, which I think is really valuable. So I would definitely recommend it. It takes up a lot of time, but ultimately, I think it's worth it.
Awesome. Okay, a lot more questions coming in.
I want to add, I think Oxford's basically the place in the world for philosophy of physics. So like some random tutor at your college who you don't know anything about can basically be world famous in their little subfield, which happened to me. Like I didn't know one of my tutors was that big, but she was sort of the world expert in that aspect of philosophy of physics. So yeah, it's like an Oxford specialty.
Can I mention, in case you haven't noticed, if you're applying philosophy of physics, physics and philosophy, or maths and philosophy, there are only a select few colleges that offer it, which are Balliol, Merton, Pembroke, St Hilda's, and Magdalen, and Brasenose. That's it. There are 6. So make sure you apply to one of those. Otherwise, it'll be quite embarrassing.
Okay. Good knowledge there. Somebody says, do you need to do both ENSA and STEP if you want to do maths with physics? No, you only need to sit the STEP. but they might ask you some like physicsy questions in your interview or mechanicsy questions in your interview. Somebody says, I'm struggling to pick a fourth course for NatSki. Do you have any advice? Presumably you've already applied, I'm guessing. This is George. I don't know if you want to add any more to your question, but Daniel, the way I'm reading this question is, during your application process, you have to let them know what kind of modules you want to do. I guess, George, if it would be helpful if you could say what your other thoughts are, so that we can give you some more sort of ideas. And we'll come back to that if that's okay, Daniel.
Yeah.
What would doing 4 A levels, i.e. maths, further maths, physics, and chemistry, increase your chances of admission at Oxford? I would say probably no. And you might also then end up getting higher grade requirements. That's on the one hand. If you're very confident with them and you love your subjects, I wouldn't say it's a bad thing either to do 4, because otherwise, if you end up just doing maths, further maths, and physics, that's basically like maths, further maths, and applied maths. Essentially, it's like a lot of maths. It's not very broad. So I think, having that 4th subject can increase the breadth of what you're learning. And if you love and you're good at everything that you're doing, then I don't think that doing 4 is a bad idea. But if, on the other hand, you feel like your grades could suffer by doing 4, then I wouldn't recommend doing 4. Does anybody have any further thoughts?
I was going to say it depends which one is the 4th. If chemistry is the 4th, then I think it's good if you're really interested in it, but it's not. I'm not sure it makes your application actually better than if you had 3, except maybe natural sciences. If your 4th one is further maths, and I think it's just a straight up. Like if you're going to do chemistry and physics anyway, then it's better to do further maths than not.
Yeah, definitely further maths. And it links into the next question: is a physics degree at Oxford a lot of maths?
Yes, it is.
It is. It's very mathematical.
First year you do more maths than physics, because later on in the course you do mostly like quantum physics, and that is really math intensive. You need really solid math skills, and you learn all of those in the first year. So the first year is math in the vast majority, and then you just keep up the math. You never do less than half of your course being math.
Okay, yeah, Daniel, I don't know if you just want to speak about the maths content in natural sciences.
In Cambridge as well, the first 2 years are kind of dedicated to building up your math skills for physics. So it's really important to have a fluency in them. And then I think your third and fourth years, if you plan to stay on, they're just purely your subject. So having good math skills is definitely important for the first 2 years. They have a lot of content.
Okay. Then we've got a question, which is, what is the difference between the physics from the natural sciences tripos and the physics from the maths and physics course? Does the former have much more practical physics? So all I can tell you on that I am aware of is the physics that you do as part of the maths and physics course is a part of, like, it's a subsection of what the natural scientists do. You actually go to lectures with the natural science students. Obviously, Daniel might be able to tell us a bit more.
Yeah, I think because of maths and physics as well being covered mainly by mainly the maths department would be your kind of home department, but like Carol mentioned, they share lectures with us. They come at the physics or applied modules more from a very mathematical point of view. So less about intuition, not in a demeaning way, but more about if you understand the maths and you can do the physics that they do in there. Whereas I think the natural sciences physics tries to build more of an intuition into what you're doing. So you do need a lot of maths, but they try add the intuition part.
So yeah, and just in terms of quantities, I think if you do maths with physics, it's 3/4 maths and 1/4 physics. That's how it works. Does the MAT have physics-like questions, even though I want to go into a pure maths course? No, the MAT doesn't really have many physics-type questions at all that I've ever seen, unless anyone. Chris, do you know any different?
No, I've never seen anything I'd call physicsy at all.
Okay, then somebody says, I'm aware that I've been learning a lot of subjects that don't really come up in A-level maths, such as multivariable calculus of variations and matrices, etc. Considering that I think these topics I want to look into take a lot of time and may decrease the amount of time I take in exam preparation, how important are these tests relative to interviews? So I'm actually a bit confused about the question. This is Janet, and I would appreciate a little bit of clarification if you could. So when you say you've been learning a lot of subjects that don't come up in A-level, is that in your own time? Or is that as part of your degree? Or I don't know if you already started your degree. I guess not. So is that just extra learning that you're doing? And the second question you ask is, how important are tests relative to interviews? I would say they're basically 50-50. They're going to be judging you on both. I would say it's like personal statement 5%, interviews 45, test 50, roughly. I mean, obviously they're just rough numbers, but that's how I would class the importance of the tests. But yeah, if you give me a bit more clarification on that, we can go through that. Somebody says, is AS further maths good enough, or we still have to do more work over the year 13 summer? I think it could still be helpful to do more work, which are in some modules that you won't have done. But you definitely will have more of a head start than someone who hasn't done any of those further maths modules. Somebody says how difficult we say the NSAA test is. The question you showed us is much easier than the PAT example. Yeah, as I said, the actual questions themselves aren't that hard. It's just the sheer speed with which we're expected to do them. Do you need A-level philosophy or religion and ethics to do a physics and philosophy degree? I believe the answer is no.
And the answer is no. You do everything from scratch.
Okay. How will you get access to the PAT or the NSAA test in November? You have to apply through your school, which is normally an examination centre. So if you're in the UK, if you're not, you probably still apply through your school. There'll be like an exam centre and they can sign you up. I'm not too familiar with the process. Somebody says, I do biology and physics and don't do chemistry. Does that put me at a disadvantage if I apply to the natural sciences? So Daniel, maybe I'll direct that at you. If they do biology and physics but not chemistry, would they be at a disadvantage?
I don't think so in terms of like strength of application, but it might be a bit of an administrative issue. But I think you should be okay. I think it'd just be hard for them to organize
administrative in what sense?
I think just because whenever they get interviewers, a lot of people either fall into the physical category or the biological one. It's rare. I think it's rare. If I've not really heard of anyone doing physical and biology, so it might be best to pick one, but then you might be able to take a biological module when you get into.
So I think what they're saying is that they do biology and physics at A-level.
Oh, so is that not to pick that at NSAA?
So they're saying I do biology and physics but don't do chemistry. Would that put me at a disadvantage if I apply to natural sciences? That's the question.
No, I don't think so. And it depends on what science you want to go into. So either if you do biology should be sufficient for biological. I think chemistry would be preferable with that sense. But then if you do, they don't really mind.
Okay. I think what I would recommend to you is actually phoning up the college or university and actually having a chat with them, because you'll get a much better answer than from us, I think, on that specific case. How should you search for a job in physics after you've gotten your degree? So I'll just quickly answer that and say both universities have really good career services. So that's one thing you can do. And also at both universities, there are consistently like networking events with big companies. There are like careers fairs you can go to. So there's lots of opportunities to kind of get in touch with employers. Does taking maths or physics make a big difference to your future career? I guess it depends what you're comparing it to. I mean, you know, a mathematician or a physicist has good quantitative skills, good problem solving skills. If you're doing philosophy, obviously good really good communication skills as well. So I think there are a lot of skills that these degrees bring that would be very valuable to an employer. I don't know if anyone wants to add anything, but if not really, then that's fine. Only add something is really valuable just because of time. Somebody says they've been doing a lot of online resources during quarantine, such as Khan Academy. Okay. Right. What I would say is I would really think you need to do a lot more maths and physics problem solving on A-level material, but outside of typical questions. I find this quite a lot. People watch MOOCs or do extra learning on like new topics, which are like, say, university level topics like multivariable calculus, or as you said, calculus of variations, which, you know, I didn't do until my second year of uni. But I think it's less useful to do that and more useful to find problems which use knowledge you already have and make you think rather than learn. So we want to go deep into the subject rather than broad, is what I would say. Go on, sorry.
So I think Janet, building on the previous question.
Yeah, I was
I think if you're doing that for the interview preparation, as Pavel said, that's not really what interviews are about. They're about getting you to use your existing knowledge in new ways rather than you trying to bring in things that you've read about elsewhere.
Yeah, exactly.
Like 50% of interview questions are just mechanics questions that are harder than A-level.
Exactly. Yeah, I would really try to stick to things which test stuff you already know, or maybe you have to learn a couple of new things, but I wouldn't go into whole new areas of study necessarily. What sort of problems and questions do you provide weekly in your mastermind? So this is exactly the type of question we provide. We provide questions on things you should have studied at school, but are quite differently phrased, or test you in a new way, or combine multiple topics. So that's the kind of questions we'll be looking at in our weekly mastermind sessions. Somebody says, if I apply to Oxford Physics and also a course in Imperial that requires math or STEP, do you think it'll be quite hard preparing for 2 assessments? So Nanami, if you could give me more information, because the MAT and STEP are usually used for maths or computer science. So would you be applying for Oxford Physics and another subject? If you could give me more info, I'd be grateful. Do you have to have done English or an essay-based subject to do physics and philosophy? Giacomo.
No, you don't have to have done anything. If we just look at the application process, the only difference is you'll have a couple of philosophy interviews, and in them they're really just testing the way you think. So they'll give you a sort of situation and ask you what you think about it. You'll express an opinion, then they'll try and break you, and they will win because they're smarter than you. But they're trying to work out how you wriggle out of holes, how you justify your opinions, and how you defend your argument. So essay-based subjects might help you with that. But if you're just an argumentative person, you might have the skills anyway. Again, reading philosophy books helps. I read a very good book called Language, Truth and Logic by A.J. Ayer. That taught me everything I needed to know for the interview. It's not knowledge that you need. It's more a way of thinking. It's a way of approaching particular questions in a sort of critical way and coming up with counterexamples or just arguments to back up an opinion. That's what they're looking for. Once you've got in, again, you don't need any prior reading that you've done in A-level, because you'll have all the reading you need to do there before you write your essays, but you will be writing essays. So you need to know how to write an essay. There are people in my course who didn't do any essay writing subjects, and they do fine. That's probably because philosophy essays aren't quite the same as, say, history essays. They're a lot more analytical. They're very they're almost mathematical in nature. You sort of take a hypothesis and you test it until you come to a conclusion. So if essay writing isn't your forte, you might still enjoy philosophy essays. The only real way to find out, in my opinion, is to do a bit of reading, see if there's sort of questions that you would want to write about.
Great, thank you. And there are some, like our book, The Oxbridge Formula, does contain quite a lot about philosophy. It's got a whole chapter of philosophy, so feel free to check that out as well for other resources and kind of an idea of what an interview would be like. Somebody says, did you have any problems with your confidence? How could we improve our confidence? If anyone wants to add to that. I think ways you can improve your confidence is just doing practice. I mean, practicing and like it and taking your time over it. So we've emphasized right now how time pressure some of these exams are. But, you know, if you're starting now 10 months before, you have the opportunity to spend a long time on a question, to do the thinking, to do the reflective reflex, to spend maybe 2-3 days on one question and really understand it. And when you start doing that, you will naturally gain confidence because you know, you'll be really thinking deeply into the problem. Also, I mean, obviously, another way to improve your confidence is by seeing how somebody tackles a question. And, you know, I think that's one of the real advantages of our program. You're with tutors who can obviously explain things to you. So that can improve your confidence. You get access to videos where real Oxbridge tutors are kind of going through questions. And so you get to see the inner workings of their thought process, just like we've shown you today. You could see exactly what we were thinking when we were going through that problem. We've tried to design our course in such a way that you can try and get into that mindset, and so that will, I think, add to your confidence. And you also be with other people who like the same subject as you. You can discuss it with them, and I don't know, maybe that could also give you confidence as well. So I think really just doing lots of questions and getting good support and guidance would be ways. I don't know if nobody has anything to add, I can move on.
My first instinct was to say practice. So yeah, I just disagree with you.
You don't disagree, yeah?
Yeah.
Great. Could you give examples of what you could do in the future after you've done a physics or astrophysics degree, such as what job to go into or further education?
I'm a software engineer, and most of my colleagues did maths or physics.
Okay, so yeah, software engineering. I think anything like financial would definitely be an option. It's highly quantitative. We already discussed potentially engineering. Then obviously there's teaching. There's going into industry. I'd be happy for anyone else to contribute.
I was going to say finance as well. For some reason, they're really interested in physicists. Any kind of sort of like any kind of management, like the civil service is looking for scientists. Like most positions that don't require a specific degree, like I don't know, medicine, you could probably have a go at as a physicist.
Yeah, I would say it's, there's a lot of skills you learn that would be very valuable to employers. So somebody says, I think
even in medicine, you could be a radiologist. That's an official route.
If you did do medicine, or if you
did physics.
Oh, okay. By taking up a lot of time, does it eat into? So I think she's aiming this question at you, Giacomo. When you said your degree takes a lot of time, does it eat into hobbies? Could you still say have 8 hours work, 8 hours hobbies, and 8 hours sleep?
That depends on how good you are at time managing and how quick you are at reading. I do a lot of hobbies. I don't do a lot of sleeping.
Okay. By the way, guys, I think sleep is really important. As someone who hasn't slept a lot, like over the last few years, I'm realizing I wish I'd slept more because it's bad for your health. So, yeah, I think what the point Giacomo made about being fast at reading, I get the impression that philosophy is a very reading heavy course. So if you're good at that and you're fast at that, and you can, write an essay quickly based on what you've read, it would probably be easier for you. I don't know, Chris, if you want to add anything.
Yeah, agreed. One thing I'd say is that often you can, once you're at uni, you can continue thinking about problems while you're doing something else. So like sometimes if your hobby is a sport or something where maybe you're physically active, but it's not like an intellectual activity, then you can be thinking about that week's problem set while you're playing squash or whatever you're doing.
Yeah, and I think it comes back to the idea of like, it's just like percolating in your mind, and you can subconsciously think of answers to problems. So that's why I think having time is good. But also what Chris said, that you can, while you're going for a walk, you can still be thinking about the maths or the physics. Can physics and philosophy get me into engineering? Because physics and philosophy sounds interesting, but I want to do engineering. I think we've kind of covered that question already. Would you say?
I'd find it highly unlikely to actually be an engineer. You could be a manager or consultant in an engineering firm.
It is a very theoretical course.
Okay, all right, great. Considering applications, I think that this is going back to the question on somebody was trying to look for a fourth option for their physical natural sciences. Maybe Daniel, if you could just talk about some of the physical natural sciences options that exist for first years, that might be helpful.
Yeah, so I think most people tend to take the route of maths, physics, chemistry, and science. So that's a very common combination. You can also take computer science, and then I think earth sciences as well. But then a lot of other modules are biological. However, even if you are on the physical strand, you're still able to take some of the biology ones, because natural sciences in first year are grouped together. So you're ranked against each other. It's the whole natural. So even if you want, you can take a biological module if you want as the fourth one, something that might not have done before. They teach a lot of content from scratch, so you shouldn't be advantage.
Yeah, you're cutting out slightly. I don't know if anyone else is feeling that way, but we can come back to that in a second. Yeah, amazed. There's still 105 people on the call, so thank you all very much for your patience. We'll look to. There's a few more questions left. We're looking to get through all of these, and thank you again for being here at the end. Quick reminder, if you're interested in booking a consultation, you can do so by scanning the code or putting that link in. You just fill out a short application form, and then you can book in a call with a member of our team. And you'll get to see what options there are in terms of programs for you going forward. Somebody says, I want to do designing of technology as well as the theory and experiments in physics. Is it possible with Oxford Physics, or is there a more suited course for me?
I haven't quite understood.
One course I'm thinking of, so they're saying that they want to do like technological design as well as like physical experiments. I was thinking maybe material science. I don't know.
I don't know anyone doing material science. It's worth looking at all of the courses in detail. On the website, you can see what you'll do every year, and it's got a breakdown, and it's really, really helpful. It's actually quite clear.
And in our book, I should add.
Oh, okay.
But it's probably, you get more information probably from the websites once you do more research.
I was going to agree about material science. They do actively research new technologies as long as they're related to materials. In physics, you can design, say, experimental apparatus, but it kind of depends what you're talking about when you talk about technologies. It's got to be something that's relevant to sort of cutting-edge physics. If it's going to be something you're researching.
Okay, differences between NatSci and Oxford Physics. Anyone want to, either of you guys want to sort of, obviously one difference is that you don't just do physics. In natural sciences, you could do a bit of chemistry, a bit of material science, and so on and so forth. But maybe just comparing the actual physics, do you guys know of any, obviously you haven't been to each other's universities, but are you aware of any major differences?
I don't know anything about Cambridge.
Yeah, I don't know much about Oxford. Cambridge, you might learn slightly less as you're doing 3 other modules in the first year, but I think by second year, if you pick only physics, you kind of catch up with Oxford. But that's just me thinking. I can't confirm that.
Okay. All right. Well, there you have it. I'm currently in year 12 doing these. Okay, sorry. I'm particularly interested in astrophysics. Should I look more into Cambridge or Oxford? I know that Cambridge have part 2 and 3 astrophysics, but I've also seen that there is an astrophysics major option for the 4th year Oxford Physics. So I'm just wondering if one is considered stronger than the other in that particular field.
I know there are modules you can take, not just in 4th year at Oxford. But they are just modules. It's never the main focus until your 4th year. And I can't compare to Cambridge.
Cambridge, you can only take astrophysics from 3rd year, essentially. So
3rd year?
From 3rd year, yeah. So you're only on the normal course until, and then 3rd year you can choose to switch.
Okay, so it's kind of like a specialism of the course, essentially. Yeah. And then, okay, that makes sense.
Just in terms of strength, I think it tends not to matter that much at undergraduate level anyway. I think Cambridge has a bit of a reputation for, say, cosmology, but that's not all of astrophysics. So it might, but if it's undergraduate level, there's probably not a noticeable difference.
Okay. Somebody says, I would like to do an engineering degree at Cambridge. Is it more important that we do well over all of our subjects? And they say, I'm doing IB, so I have several subjects. Or is it more important to do well in physics, maths, and further maths?
I know some people who had very high offers required for Cambridge if they're doing the IB.
So you mean that means across all subjects then, doesn't it?
Yeah, I know someone who well, okay, to be honest, he was doing a very odd range of subjects and he was applying for Cambridge Maths, but he got asked to get a 44, and he did. But it's not uncommon for Cambridge to ask a 42 or above. Well, it doesn't usually go below 43, but a 42 or a 43 is a common offer.
What's the max score? Is it 45?
45, yeah.
Okay.
And I think 42 might actually be standard. It is. I know it's in the book, but
yeah, getting a 42 requires, just 1/6 and then 2 in core. So you need to be good across the board.
Okay, good. What's the difference between ENGAA and NSAA? So I think, as I said already, that the questions are basically the same. They're literally the same questions, but they're just in a different order. I think there might be 3 or 4 questions which are different between the papers, but they are very, very similar. Have you had to deal with imposter syndrome? And if so, how did you overcome it? I would say I have, but not when I was applying to uni. I think for me, it was starting a business. I had lots of imposter syndrome with that. How did I overcome it? I think when I finally realized that like not everybody's like judging you and you're doing a good thing, then yeah, when I finally like decided to just make, I got over it, and then everything was fine, if that makes any sense. So that's what I would say for me. I don't know if anybody else has.
It is really common. Because everyone comes from backgrounds where they were the top of the class and suddenly they're not. Personally, it wasn't that bad for me. What was very strange is I went from being the academic person at my school to the sporty one at Oxford. And I'm not very sporty, so that's a lot of Oxford. So it does take a bit of getting used to. You sort of need to find a different new space for yourself. And yeah, you got to get used to not being the smartest person anymore. But in general, the atmosphere is really accepting. And everyone knows that everyone else also has imposter syndrome. So it's not something people really suffer from.
Okay, it's just kind of across the board. Okay, interesting. Daniel, do you want to add?
Yeah, I think for the people that do suffer from it, it's just best to remind yourself that you have to go through quite a rigorous process to get into Oxbridge. So I think if you do suffer from it, I don't think I've but I know people have. Not as a cocky way, but I just know like you just have to remember that you did quite a lot to get in.
Yeah, you do deserve to be there. Like you had to prove yourself.
Yeah. Exactly.
Okay, Chris, do you have anything to add to that? Okay. All right, cool. Sorry. Okay. I'm not sure if it was Imperial, but I saw some unis require STEP or MAT or something like that for joint honours of maths and physics. Yeah, definitely. If you're doing maths, it's not maths and physics. It's not joint honours. It's maths with physics. So, like I said, it's mostly maths and a bit of physics. And yes, because it's a maths course, you have to sit STEP for that. Maths with applied maths and I think this was a previous question. Let me just go back to it. I can't remember what it was now. Somebody says, I want to apply to Oxford Physics and also a course in Imperial that requires math STEP. Okay, so what you want to apply maths with applied maths or mathematical physics in Imperial. Would it be too much? I mean, look, I know for mathematicians, if you're applying to maths at Cambridge, you have to sit the STEP and you have to sit the MAT if you're applying to Imperial, and you might have to sit the TMUA if you're applying to Warwick or Durham or something. So there are many people who do multiple tests. I mean, it is challenging, yes, but I guess it gives you more options across the board. So I wouldn't let that put you off. And in fact, it's just doing more problem solving. So I think that, it's going to preparing for one will help you preparing for the other one. Unless, yeah, Chris, if you want to add.
So I think with MAT and PAT in particular, there's kind of a logistical problem that they normally take place on the same day.
Oh, yeah.
They might. So it would be a long day if you had to do, say, one in the morning and one in the afternoon and be supervised over lunch or something like that. Last year, I can't remember if they took place on the same day or not because the tests were split up. But that wasn't typical. I think if it's, say, PAT for Oxford and MAT for Imperial, I would probably, I don't know, I might recommend doing the PAT for Oxford and then not doing MAT, explaining that choice to Imperial, and then taking STEP, because there'd probably be a step over.
Well, okay, first of all, you can do both exams on the same day.
You can.
But it is a bit of a stressful day, I guess. So, yeah, I don't know, like STEP now, Chris, there used to be step 1, 2, and 3, and now step 1 doesn't exist anymore.
Yeah,
the step requirements have become much more difficult. So if I don't know, I think if you have enough time to practice, the thing is, if you're more interested in physics, then the MAT is quite, it's relatively difficult. in terms of
the other thing about the maths is it has a very unique style, which is kind of different from the maths in the PAT. So you would have to do a lot of past paper practice for both, just to get used to both styles of question. I don't know, maybe you could ask Imperial and see what they think, but then the danger they'd just tell you to do math.
Yeah, I think that's a difficult one. It's a tricky one. So yeah, even I might have said step if step 1 still happened, but now that step 1 is cancelled, it's been like discontinued by Cambridge, I would be a bit like, step 2 is definitely getting a lot harder. So, I think maybe have a look at a step question. I think the best thing to do would be for you to actually have a look at the papers and try them and see. We don't know your level. We don't know anything about you. And you might be really good at all of them, in which case, you won't have a problem at all. But otherwise, I might do what Chris said and check.
Yeah, the trouble is steps changing this year, in the sense that step 1 is going, and we don't know what Imperial would make with step. It does have the mechanics section. I don't know if that would be any more accommodating for someone interested in physics. Yeah, you'd have to just test out the papers, I suppose, and see how you feel about them.
Okay. What, in your opinion, is the best physics, best college at Oxford for physics, in your opinion? In your opinion?
I mean, everyone applies to Keble because you have Keble, you have a road, and you have your lectures. That's why it's very popular. The brickwork looks like a lasagna, so I don't know. I don't think it's the best college. Ultimately, for physics, they're all fine. There'll be a great physics tutor at any college.
And remember that the main course is taught centrally in lectures. So, obviously your tutors will be with you for a couple of hours a week. A lot of the learning you're going to do is going to be in lectures anyway, which is common to all the unis, colleges. Someone says, does Oxbridge help with funding for beginning a business? I mean, I'll be honest, I'd never wanted to be an entrepreneur when I was at Oxford. So I don't know the answer to that question, because it was quite a few years after I left that I started a business. You guys might have more ideas than I do. I think there is a lot more available, but I'll let you guys.
Yeah, they do. There's the career service have some funds. Some other individual societies manage to get funds, but they're for more specific things. If you want to do, I don't know. But if you want to start a sort of generic business going through the career service, you can definitely get funding. It's not. Oxford isn't the best university for startups. That tends to be, most of them tend to come from like UCL. But yeah, there is money available.
I do know a lot of entrepreneurs. Like, I think compared to Cambridge, I feel like people I knew who were Oxford versus Cambridge, I feel like Oxford's definitely more entrepreneurial, is my thinking, is my opinion.
And just better.
Specifically in technology, I think it might be even, because Cambridge has this partnership with local businesses for technology. But I don't actually know how effective that is for students.
I wouldn't say that's necessary for a startup. I don't know, but maybe. Do you know anything about this, Daniel?
No, I've not really heard much about the funding part, so I can't help on that front.
That's fair enough. Let's go to the next one. How much did financial factors weigh in your decision to apply to Oxbridge? I mean, I applied when the fees were not £9,000. I think for me, it didn't make as much difference. I'm quite old, but I don't know if any of you guys want to say, given that you...
I think it should weigh in favour, as in it's probably on average cheaper to attend Oxford or Cambridge than, in particular, a London university. But also, I think most universities are charged the top rate of tuition fees because the accommodation on average is cheaper over the whole year because the terms are shorter. And a lot of stuff is subsidised. And colleges often have financial support for various things. So it might be worth asking the college you are interested in what kind of financial support they apply, but normally the answer is some, or even lots. So it's worth bearing in mind, but it tends to be something that actually points you towards Oxbridge rather than another, say, Russell Group university.
Yeah. Does anyone else have anything to add on that?
Yeah, definitely, because of the short terms, especially my overall rent for the year is a lot cheaper than people at other unis. And I think as Oxbridge and are richer than a lot of other unis, they can give more financial support if you do need it.
So you're saying you just cut out. I think you said Oxbridge colleges are like more wealthy, so they can give more financial support.
Yeah, then if you were at other institutions, at least as far as I'm aware.
Okay. Anything else to add?
It doesn't feel cheap, but I will second Chris's point on financial support. In all the colleges I've interacted with, there is plenty available.
Good. In the PAT, would you write your answers on an answer sheet or in a separate paper? I think you write it on the answer sheet. You do it on the actual booklet. Can you confirm that?
That was true when I sat it. Yep.
Okay. Can you do the MAT and PAT? I think we've answered that one already. Can you apply for a course that requires PAT and then change your mind to a different course that requires a PAT after taking it? Well, I don't know if you can change what your course you're applying to like midway through the application process. I know people who changed courses that they were doing while they were at like Oxford, like say they did half a year in first year, and then they wanted to change, but the conditions for them to change were that they had to get a first in the subject that they were doing. So it's not like you apply to an easy course and then change to a harder course. You actually have to show that you're really good at what you do in order to be able to change. That's what I remember. Anyone else?
I knew someone who changed from PE to maths and philosophy, but he had to attend all the lectures for both, which isn't as bad as it could be because some of them overlapped. But for the first term or so, he had to attend both. He changed his mind.
Okay, in case he changed his mind.
Yeah,
okay.
I've heard of. Daniel maybe can say more about this, but I've heard Cambridge is often quite open to people changing after the first year between, say, maths and computer science, or I don't know, natural sciences and maths or something like that.
Yeah, they're quite lenient at Cambridge. I know at least about 4 people that have switched courses. So one person entered natural sciences and then switched to economics, and then others have gone from physics to engineering, or even I think to maths. So as long as you can kind of prove that you'll be, I think they want to limit their dropout rate, so they are kind of lenient, but also they don't want you to be really bad at the course. So they'll give you they'll re-interview, but they are quite lenient.
So you'll be so you kind of have to go through the admissions process again. Okay.
Yeah.
I don't think you should ever go in with that intention, by the way.
Yeah, agreed. Completely agree. Yeah, apply for the course you actually want to do. Would taking computing for advanced hires be helpful for the coding aspect of physics?
It depends on. So when you do computing for advanced hires, that's presumably in Python. You can use Python starting from the second year.
Yeah. I think they're talking about Scottish hires, but I don't know if you know that much about this. I don't know much about them.
It'll almost definitely be Python.
Okay.
I'd be very surprised if they're doing a different language.
Okay.
If it's a different language, raise another question. But assuming it's Python, you can code in Python for starting from the second year, but in all the coding in the first year has to be in MATLAB. So yeah, having some coding experience helps. Obviously, transferable skills, but it's not essential.
Okay, and then they said if I maybe didn't finish the question. They said they're taking 4 instead of 2 or 3. Physics, mechanics, general maths, and computing. Oh, I don't know that much about the Scottish system, to be honest, but I think I would just take what Giacomo just said, as it would be helpful for the physics coding. That is the last question. So yeah, we have come to the end of the webinar. So on behalf of Daniel, Chris, Giacomo, and me, thank you very much for attending. I hope you learned and enjoyed it. And hopefully that gives you some motivation to go and do problem solving from now to maximize your chances of getting in. Yeah. Okay, if there's nothing to add, then take care. Bye.